Hello everyone and welcome to the day 2 workshop on Liutex and third generation of Vertex identification for engineering applications, which is an integral part of Aerospace and Aeronautics World Forum. So now we are starting the day 2 workshop of this meeting, and now we'll begin with our first talk.
If you we may talk after the conference. We will cancel. I think we will cancel group meeting for today.
I need to go to university after the conference. I have class.
Yeah, it doesn't bother. But you have something today?
I mean, I have class. I have class.
You have class. Okay. What time?
9:30.
Oh, 9. Oh, no. I just after the meeting means afternoon. So
okay.
It's not in the morning. Yeah, not this your session. The meeting until 11. I think 11 o'clock. We can talk about afternoon.
Oh, my class.
Yeah.
9:30 to 10:30 my office hour, and 11 to 12 my class time, and 12 to 1 that's the math clinic conference.
Whole day.
Yeah.
But I think I will send a message. We will cancel the group meeting today. Yeah.
Okay.
Because it's too it's too busy, everybody.
Yeah.
Hey, this is Bindu, the webinar host. So once again, I want to welcome you all for the day 2 of the workshop. So now from here, Dr. Wu will be taking it forward. Thank you.
Okay. Hello everyone. My name is Yifei Yu, and I'm the host of the first section today. Yeah, it's time for us to start our conference. The first presenter of this session is Dr. Yiqian Wang, and his topic is Liutex in homogeneous isotropic turbulence. Let's welcome Dr. Wang.
Hello, everyone. Dear host, but I'm not allowed to share screen. So at this time, I cannot share my screen because I'm not allowed. Webinar host, you still here?
Dr. Wang, when you're launching your Zoom, you need to check, open with your system video, including the audio. Will be
So I have to leave the room and enter again.
Could be just a moment, please. I will just put you in loop with the technical support. Just a minute.
Yeah, I think the host disabled the participant screen sharing. So if you are the host of the conference,
so maybe others can try to share the screen and see if you can share the screen.
Well, I tried. I faced the same problem.
Okay. So
just a moment, please.
Okay.
I think I can share the screen now.
Yeah, now please try once again to share the screen, Dr. Wang.
Okay. So
Oh. Now, are you able to share your screen?
I'm trying to. I'm trying to. I'm sorry. It says I have to give it privilege. Okay, it says I have to leave and re-enter. So wait for a minute.
Okay.
And can you see my screen?
Yes.
Yes.
I will play the video and tell me, can you hear the voice of the video? Hello, everyone. This is Yiqian Wang from Suzhou University. My topic today is Lyotex in homogeneous isotropic turbulence. In the talk, I will first give a very brief introduction to the Lyotex system, and then we discuss the intermittency and similarity of Lyotex in homogeneous isotropic turbulence, HIT for short. Finally, conclusions and discussions will be given. As we know, vortex is a very common phenomenon in nature and engineering. For example, tornado is a typical, very strong vortex, cosmic nebula that made of cosmic dust, often exhibit vertical motions. The wingtip vortex determines the takeoff and landing frequency in an airport. In addition, the vortices formed above a swept delta wind enhances the lift, and therefore the term vortex lift. We also know that turbulence are made of many vortices of different scales. The helicopter rotor would also induce many vortices, and the dynamics of those vortices are very important for the design of helicopters. A famous quote by Kuchman says, vortices are the sinews and muscles of fluid motion. Therefore, the definition of vortex is a very important issue in fluid mechanics. However, even with many scalar methods, the definition of a vortex remains an open issue. The problem of these second generation methods includes threshold problem, unclear physical meaning, shear contamination, etc. Note that here we have classified the vorticity-based methods as first generation, and those scalar methods as second generation. To overcome these issues, Professor Chaoqun Liu and his team introduced the omega method, the Liutex vector, and several vortex identification methods based on the Liutex vector. We collectively refer these works as the third generation of vortex identification methods. According to Google, the omega method paper has been cited over 200 times, while the Liutex vector paper has been cited more than 170 times. Here we present the explicit formula of Liutex vector. The direction of Liutex vector is a real eigenvector of velocity gradient tensor. represented by the lowercase bold r in the equation. The magnitude of Lyotex represents twice the angular velocity of the rigid body rotation part of the fluid motion, and can be deduced from vorticity omega, real eigenvector lowercase r, and lambda ci, the imaginary part of complex eigenvalue. On the other hand, homogeneous isotropic turbulence, HIT for short, is an idealized model of turbulence introduced by G.I. Taylor. In this study, we are using the DNS data for HIT by Cadasa et al. The data was obtained by solving the incompressible Navier-Stokes equation. Forcing at the two lowest wave numbers has been made to make the flow statistically stationary. On the left hand of the slide is the isosurface of Lyotex magnitude to represent vertices. Note that here we only show the box. The shown box is pi times pi times pi, which means it is only 1/8 of the whole computational domain. It is shown in the left figure the distribution of streamwise vorticity component, omega x, and in the right figure, the streamwise Lyotex component, Rx. We can see that Rx is more concentrated on islands of high magnitude, and omega is more continuously distributed across the plane. It is found that 40% of the whole computational domain is void of Lyotex. According to the definition of Lyotex presented above, the magnitude of Lyotex is always smaller or equal than that of verticity. However, this relation does not carry on to component directly because of the directions of Yotex and verticity are generally different. We have found that 7% of the whole computational domain has larger Rx than omega x. The probability density function, or PDF, of Rx and omega x are shown in this figure. Note that only the 60% volume with R larger than 0 has been taken into account when obtaining the PDF of Rx. Even though we can see that the PDF of Rx is significantly more concentrated near 0 than omega x. That means compared with omega x, Rx has more probability to be near 0 and seldom becomes large. Therefore, Lyotex is more intermittent than vorticity in HIT. Actually, the vorticity has been viewed as an intermittent variable in turbulence. Intermittency is used to refer to the uneven scattering of turbulent fluctuations and has been argued to be a reflection and an indicator of coherent structures. Here, we adopt the definition by Jimenez for intermittency. For quantity chi with PDF p chi, f chi, the volume fraction of data above a threshold k0, can be defined as p chi integrated from chi0 to infinity. And the fraction of chi above that threshold is f chi equals chi times p chi integrated from chi0 to infinity. divided by the average chi. F chi can be viewed as the fraction of contribution from chi greater than chi0 to the average chi. If a threshold chi0 can be found that such that V chi is relatively small, while F chi is relatively large, which means the average chi is relatively determined by a small fraction of concentrated large chi. The variable chi is then considered intermediate. Here we show the Vx, Fx, V chi, F chi diagram for Verticity, Lyotex, and Lyotex that are not zeros. Obviously, R is more intermittent than Verticity, as indicated by the gray patch, with a relatively small volume fraction of 20%. The fraction of R above the corresponding threshold reaches 75%. The intermittency of the Lyotex magnitude means that the strong rotational motion is concentrated in a small volume fraction, and therefore we can expect that the isosurface of Lyotex can isolate the rotating region. Here we show again the previous figure of Lyotex isosurface. The threshold is 18 times square root of average squared Lyotex. From the above discussion, we can expect that the large values are inside the isosurface, and outside the isosurface, the Lyotex magnitude would remain very small. Here we show a 3D energy spectrum of velocity, verticity, and the Lyotex vector. Kappa here is the wave number, eta is the Kolmogorov scale. Dotted lines with powers of 1/3, -5/3, -10/3 are added in appropriate places. It is shown that for HIT, the turbulent kinetic spectrum E follows the -5/3 law in the inertial subrange as predicted by Kolmogorov. The energy spectrum of vorticity, or the entropy spectrum, follows a 1/3 power law in the inertial subrange. Since Lyotex and Verticity have the same dimension of 1/2, it is not surprising to find that the energy spectrum of Lyotex also follows a 1/3 power law in the inertial subrange. A distinctive feature of the energy spectrum of Lyotex is that it follows a -10/3 power law in the dissipation range, which agrees with the findings of Shear et al. Here we show the streamwise 1D energy spectrums in turbulent channel flow. The four figures are energy spectrums of velocity, vorticity, Lyotex, and a second generation method, Q method. Among the power laws illustrated in HIT, only the -5/3 law of velocity and -10/3 law of Lyotex remains to be observed. However, we can see that turbulent kinetic spectrum only marginally match the -5/3 power law in a narrow wave number range. For the Lyotex spectrum, although their distance from the wall are different, they basically follow the -10/3 line in the dissipation range, subrange, except for the black line of y = 3, which is located in the viscous sublayer. To further verify the power law, the compensated energy spectrum are also given. We can see that the Lyotex spectrum in the dissipation range become nearly horizontal. And it seems that this -10/3 law is the only law survived from the wall presentation. And it might be useful for us to model the near wall turbulence. In retrospect, we have discussed the intermittency and similarity of Lyotex in HIT, power laws of energy spectrum, especially the -10/3 power law of Lyotex in the dissipation subrange are considered. It is further verified that this power law survives from wall presence and might be helpful for wall modeling. Thanks for your attention. That is all for my talk today. Should you have any questions, I will be more than happy to answer. Thank you very much.
Okay, thank you, Dr. Wang. Your speech is very impressive. And do you have any questions you would like to communicate with Dr. Wang?
Well, I think Dr. Wang analysis is more general and more theoretical because he studied homogeneous turbulence. Most of us, I think, studied boundary layer. The boundary layer has the strong shear. It's different from the homogeneous. I think homogeneous flow really is not very common in the engineering. Engineering mostly boundary layer. So boundary layer, Lyotex and Verticity, a big difference. But in the homogeneous turbulence, well, because you don't have strong shear. Yeah, so yeah, the Lyotex pretty much close to the Verticity. But from Dr. Wang's analysis, we can find there's still some difference, you know. Yeah, but more important, what I think it is for the dispersion, yeah, dissipation range, subrange. That means we talk about the dissipation subrange is mostly about boundary layer, but he talks mostly by homogeneous turbulence. So surprisingly, they are about the same. So I've been here about the same. That's the way it surprises me, because when you do the turbulent modeling, especially for the subgrid model, I think the similarity is most important. If we don't have similarity, how to model? How to model? That's surprisingly, the boundary layer same as homogeneous. That's why, you know, surprised me. As I think this is maybe a special case for boundary layer, but actually it's not a special case. It's for all the turbulence, really, including the homogeneous turbulence. Yeah, I'm not sure that my understanding is correct or not correct. Yeah, Dr. Wang knows also. So your paper is your conclusion already published in the Chinese Journal of Mechanics, right? My understanding.
No, it is
Not
under
yet.
review. Not yet.
Not yet. Okay, not yet. Yeah, but my understanding is correct or not correct. Then I say, well, this is means same. No matter is a boundary layer or no matter it is homogeneous. The Newton has the similarity law in the dissipation subrange. Is correct or not correct? I just not sure.
Yes. Thank you for your comments.
No, I just ask you. So you do agree or you don't agree? Yes.
Well, I do this research because I want to see what is the scenario in a homogeneous isotropic turbulence, and Yes, what you said is, I agree what you said is that the wall turbulence is more important, and theoretically maybe we can do something. We can do something with HIT, and in the end we will come back to the wall turbulence. It is more more useful for engineering applications, I believe.
You
Thank
talk
you again
about
for your
many parts,
comments.
intermittency, right? Intermittency is correct.
Yeah, intermittency.
Okay.
Okay.
It has intermittency. Okay. Okay.
Thank
Okay,
you.
thank you. Okay, Yu, it's your time.
Okay, can you hear me?
Yes.
Okay, good evening, everyone. My name is Yulian Jie, a doctor candidate from Shanghai Jiao Tong University. The topic of my presentation is propeller wake and noise analysis based on the third generation Vortex. Next, I will introduce from the following four aspects: background, hydrodynamic results, hydroacoustic results, and conclusion. As we all know, sound is the most effective signal underwater. Noise will reduce the stills of ships, affecting the completion of military missions. On the other hand, turbulent flow passing through the object causes pressure fluctuation and generates sound waves called flow-induced noise. It is an important sound source for high-speed ships. Oh, sorry. This is with sound. I think I will stop it. Okay, sorry. As we all know, sound is the most effective signal underwater. Noise will introduce the stills of ships, affecting the completion of military missions. On the other hand, turbulent flow passing through the object causes pressure fluctuation and generates sound waves called flow-induced noise. It is an important sound source for high-speed ships. However, the prediction of such noise is very difficult. This is because the far-field propagation model is uncertain and the huge amount of calculation for direct numerical simulation. The alternative choice, well established in literature, is represented by the acoustic analogy, which allows to decouple the fluid dynamic problem from the acoustic one. The sound field can be divided into two parts. One part describes the sound production process called the near field. The other one describes the propagation process of sound called the far field. The background idea is to treat the flow as a collection of noise sources and to describe the way pressure signals interact and propagate in the field through the wave theory. Among the number of literature acoustic analogies, the original Lter analogy represents a rearrangement of the fundamental conservation laws of mass and momentum into an inhomogeneous wave equation. Lter's work was first extended by Kerr, who accounted for the possible presence of a body in the flow field, and subsequently by Fox, Williams, and Hawkins, who developed a more comprehensive formulation in which the body could be considered in motion. Here we use the most widely used Fox, Williams, and Hawkins FWH equation. An improved Rotex or Liutex is used. Two aerodynamic benchmarks selected here, namely the three-dimensional flow around the cylinder and the flow around the rod NACA 0012 profile. The geometric information of the computation model is shown in figures. The Vertex cloud map of the flow field is shown as animations. It is obvious that the Vertex shed phenomenon of the flow around the cylinder is relatively regular with obvious periodicity, and the vertex is relatively large partition. As for rod NACA 0012 profile, due to the cylinder weak after the secondary interference, the turbulence continued to develop and the intensity of turbulence increased. So the Liutex showed stronger irregularity, and the vertex was relatively finer. Then we will show the hydrodynamic results of DTMB propeller. The DTMB 4119 three-blade propeller is selected as a research object as a well-known model widely used both in hydrodynamic and hydroacoustic fields. This propeller has a simple geometric structure and relatively detailed hydrodynamic experimental data. The basic parameters of the propeller are shown in a table. The numerical domain is cylindrical, as shown in the figure. The propeller is arranged 2D downstream of the inflow patch, and the outflow patch is 4D away from the disk. So the wake can be fully developed before reaching the outlet. The diameter of the outer cylinder is set at 3D to avoid interference with the flow of the propeller. Figure shows the comparison between the hydrodynamic coefficients obtained by the computation and the experiment and the different advanced coefficients. It can be seen that the error is very small. Here, we mainly focus on the working condition when the advanced coefficient is 0.7. The two animations give the vertex identification of the Q criteria and the Liutex criteria. It can be seen that the Liutex captures more details of the vertex. We selected three sections, y divided by d equals to minus 0.25, 0.5, and 1, plotted in the time averaged contours of axial velocity, turbulent kinetic energy, TKE, and Q amplitudes, as figure shows. The section force is dominating the upstream region, which can be seen from the axial velocity and the TKE cloud diagram. Besides, there is almost no vertex upstream of the propeller except near the hub, which is related to the small upstream TKE. The axial velocity downstream is mainly distributed in the range of the disk area, and this area produces most of the thrust force. The tip vertex weaken rapidly with the increase of the distance, but the hub vertex can continue for a long way. The TKE of the tip part gradually decreases in the downstream region, but the TK of the hub part is increasing. In the figure, we plot the pressure, the epsilon of runs and the turbulent viscosity on the three cross sections. The low pressure core inside the tip vertex can still be seen until y divided by d equals to 1. In the hub vertex, the epsilon is large, which can be considered as the area where the sound source is concentrated. Satisfactory values are also obtained for the viscosity in the tip and hub vertex regions. We compared Liutex with Verticity. The second generation Vertex Verticity has an obvious drawback. That is, there is false vertex near the AMI surface. The third generation vertex Liutex solves the problem of the false signals on AMI surface. But the false signals at the boundary still exists. For comparison, a cavitation condition is also set here. The relevant parameters of the operating conditions are shown in the table. The cavitation bubbles are as animated. Here we compare the Q criteria and the Liutex in the cavitation state and found that omega R can not only capture the vertex structure further downstream, but also eliminate the false vertex on the wall. Next, we analyze the sound field. In the near field, six near field probes are set up in the sequence from the upstream to downstream, taking the object surface as the integral surface, the dipole contribution, monopole contribution, and CFD measurement values of the 6 test points are plotted respectively. It is easy to see that the sound pressure at point A2 is the largest. No matter which sound pressure point, the contribution of the dipole is much greater than that of the monopole, and the total sound pressure is relatively consistent with the CFD measurements. At the same time, near field test points for cavitation, the results of the acoustic analogy and the CFD measurement are quite different. This is mainly because the influence of the nonlinear sound sources is not considered, and the existence of the two-phase flow also has an influence on sound pressure propagation. Here, we consider the difference between the two cases from the perspective of nonlinear sound sources. The sound source of the cavitation is longer than that of the non-cavitation, and it is more complicated near the object surface. The reason is lies in the verticity distribution. Omega R gives the consistent results. As for the far field, 4 planes are selected, and 36 test points are set for each plane. The penetrable integral surface is used to calculate the acoustic directivity. In this way, nonlinear terms can be considered. Therefore, it can be seen that there are quadrupole characteristics on the 2 X planes. This is because the quadrupole is dominant in the far field. On the Y plane, it shows a uniform distribution. As for the cavitation, the decay speed of the cavitation is less than that of the cavitation, which is caused by different verticity distribution laws. This can also be explained by the distribution of omega r. As shown in the figure, the verticity of the omega r of y1 is already small for non-cavitation conditions, while for cavitation, the Lyotex is still considerable. Therefore, the decay of the cavitation state is slower. Finally, three conclusions are obtained as follows. Firstly, the third generation Vertex recognition technology can capture more detailed vertex structures and eliminate the false vertex signals on AMI surface. Secondly, for the distribution of left-field sound sources, the vertex distribution given by Lyotex is more consistent with the sound source distribution. Thirdly, nonlinear terms dominate far-field noise. Lyotex, which predicts the vertex structure more accurately, can explain the far-field decay law better. Thank you for your listening.
Okay, thank you, Dr. Yu. Thank you for your presentation. Does the audience have any question?
Well, let me say a few words. That's a nice work. And my impression is that, well, Q, of course, can show the vertex well. It sounds to me, Q, yeah, look at your next, yeah, past it. Looks like Q sometimes mistreated the Shear as a vertex, first. Second, it sounds to me actually it's the Liutex omega method. It looks better, capture strong and weak vortices. Is my understanding correct? Yeah.
Yes, yes.
Is correct? Yeah, you can show I think some graphics. You show that. I think it's past before that. Before, I think, yeah. I see some graphics. The graphics show the it's not in the right position. Can you go up, going up? Yeah. Going up, yeah, yeah, not here. Yeah. Oh, okay,
This?
maybe past it. Yeah, maybe down, going down, yeah, going down. Yeah, I see something going down. Is it going down or going up? Yeah. Here, pay past. It's a 14. 14. Yeah. Yeah, 14. Yeah. You look at this picture. Sounds to me, Q get more things upstream and downstream, but loses something. It sounds to me, yeah. I just don't know what is this downstream and upstream for Q. And I can see your omega didn't capture this. I'm not sure what is this. And then Q didn't capture the downstream. And omega capture more structure down. I'm not sure my understanding is correct. Could it be Q mistreated some Shear as the Vortex, and Q cannot capture both weak and strong vortices. Is correct my understanding? Yeah.
Yes.
Okay. Okay, that's my comments.
Thank you.
Okay. Is there any other questions? Okay. If no other questions, let's turn to the next presentation. Our next presenter is Xiangrui Dong from University of Shanghai for Science and Technology, and her topic is Liutex investigation on rotation in turbulence and two-phase flow. Okay, let's welcome Dr. Dong.
Thanks, Yifei. Can you hear me?
Yes.
Okay. This one. So can you see the screen?
Yes.
Okay. Okay. Hello, everyone. My name is Xiangrui Dong from the University of Shanghai for Science and Technology. I'm sorry I changed my title of the topic. So I'll give a talk about the Lyotex investigation on rotation in turbulence and two-phase flow. Well, the main content of my topic will consist of these 4 sections. The first one is background, like some issues on turbulence. And the second part is Lyotex application in experimental study on turbulence. Well, next is the jobless collision by Lyotex curve method. And finally, we got some conclusions. Well, as we know that turbulence study starts from early 19th century, like Navier-Stokes equation in 1821 and the famous Reynolds experiments in 1883. And the isotropic turbulence proposed in 1953, and the concept coherent structures and bursting in 1967, and so on. Well, during this long period of time, some issues on turbulence came out, like what is turbulence and the growth mechanism, and what is turbulent vortex dynamics. Also, there's different opinions like turbulent flow fluctuation, random flow, and what has motion, what has broken, coherent structures, etc. Well, for the investigation on the vortex structures or coherent structures in turbulence, there are several vortex identification methods, which can be classified into 3 generations. The first one is Verticity, and the second one is Galilean invariant. And the third generation is a series of Lyotex methods such as Lyotex vector, Lyotex omega, and Lyotex line method. So it's based on Vorticity decomposition. Here shows the Lyotex omega isosurface with Lyotex lines, and the Lyotex magnitude gradient lines, and the Lyotex core line of a single hairpin vortex. And here list the papers for your reference. So what is the by using Lyotex method? So our work has 2 parts. The first one is the Lyotex application in experimental study on turbulence. The purpose to capture the hairpin vortex or vortex packages by using our measurements. There shows 4 measuring system arrangements. For example, the XY, XZ, and 135 and 53 degrees between the light and the plate. Well, and the meshing system is shown in the right figure. And the camera is not fixed and move with the same speed of vortex structure, so we can capture the vortex. And so there's a video shows the vortex generation and its evolution in a turbulent boundary layer by using a moving SFLE method. So the SFLE means moving single frame long exposure method. So the vortex motion is clear to observe. We know that it's really hard to give a more accurate vector field to of quantity in experimental study compared with the simulation. So and even we use the moving PIV, we made the same problems. So in this work, we try to apply the Lyotex identification method to our experimental result. Then we select the generation process of a single vortex in flow field to do the discussions. And to make sure the velocity field is accurate without much interpolation errors. And then the Lyotex and the Verticity field can be accurately accurate. So we move the pseudo vector in positive position. Well, so let's see the figure A. The velocity contour shows a strong shear layer. So this shear can also be presented by the concentration of the high verticity value. However, the Lyotex magnitude is really big, or almost equals to 0. Actually, the vortex or a fluid rotation haven't generated. Then let's look on figure C. The vorticity and the Lyotex contours in figure C. It's obvious that the high value marked number 1 and it's the vortex. However, there is actually no vortex structure in the region marked number 2, but the vorticity value is high. And there's no vortex in the region marked number 2 for the Lyotex magnitude. Okay, and we also change an arrangement of meshing system, which is 53-degree arrangement. So a single hairpin vortex structure evolution is captured by our moving SFLE method. So we can see the head, the neck, and the legs in a single frame by particle trajectories. And there's a video. Okay. Well, the vorticity, we compare the vorticity as well as the Lyotex magnitude in this figure. As is seen, the rotation region can be accurately distinguished from the strong shear layer. Then the corresponding quantitative analysis of the experimental results can be revealed by Lyotex. For example, we check the Lyotex integral and the size of the whole process for vortex generation from peer to disappear. So the whole process can be represented by these 4 states. The first one is the synchronous linear state. because during this period, both rotation strength and the size of the vortex is increasing. And in the second state, the strength is still increasing, but the size is unchanged. So this state is named as absolute enhancement. Well, during the third state, the strength keeps unchanged, but the size increases, so we call it an absolute diffusion state. And for the last state, both strength and the size are decreased and dissipated, so we call it screen dissipation state. Well, the second part of our work is to use the Liutex curve method to detect the precise of two droplet collision with a tangent angle, which is a gas-liquid two-phase flow problem. And I think we can get a good result by Liutex curve identification. Well, at the beginning, at the time one, there are two Liutex curve lines, which means they own their rotation axis before total drop fusion. Well, after that, two axes change into a single one. So there's some parameters of two droplets of collision. And the Liutex magnitude around the core line is detected at each time, and the linear decrease is founded for two droplets. After the droplet fusion, the Liutex magnitude increases with time. Okay, based on the analysis presented above, we get two conclusions. The first one, moving single frame long exposure method and moving PIV can measure the spatial temporal evolution process of vortex structures in a turbulent boundary layer. Liutex vector is applied in our experimental results for the structural localization and quantitative analysis of the local fluid rotation. And the second one is the Liutex curve line can be a good tool to express a process of two droplet collision. The rigid rotation of the droplet collision has a trend of linear decrease followed by increase after the droplet fusion. So that's all my topic, and thank you for your listening.
Okay, thank you, Dr. Dong. Is there anything you would like to communicate with Dr. Dong?
Hi, I have a question. Can you hear me?
Yes.
Yeah, and first, I think this is a pretty good presentation. I like the graphics and the simulations. And my question is, what's the major difference between SLFE and the PIV method?
You mean the two meshing method, right?
Yes.
Because actually they use a different exposure time and different for this one. For the moving SFLE, they use a single frame and a long exposure. the exposure time. It's like this. But for PIV, use multi-frame and short exposure time. And also the particles, the particles, the amount of particles is different.
Okay. Thank you.
Okay.
Well, yeah, I just say a few words. First, it looks like a very nice work. Second, from my observation, because there are several people already talked by turbulence, by MVG, by droplets. So you talk about droplets. Sounds to me they are all same feature, something like that. It sounds like you hear the 13. It sounds to me almost they first get rotation because that's the fluids. Fluids always wants to rotation. Yeah, then have two cores, and then they rotation, and then get closer, and then become one vortex. And that's always like that. That means share, rotation, pair, and one. We call the maybe vortex mixing or vortex or vortices combination, something like that. Sounds to me.
Yeah, right.
It's always
You're
like
right.
that. Yeah, that's the
So
nature.
I don't. Right, I don't know if a few people use Liutex or other Vertex identification method to the two-phase flow or the multi-phase flow, and what they're talking about what they discuss about. But I think I believe a few people do these things like. Also, we can discuss the Vertex merging in
right.
two-phase flow.
Yes, that's important. No, I don't think that not many people do it because people first maybe they mostly use the Verticity, not the Yotex. Where if they want to use a Q, they cannot get the axis, rotating axis, because the Q with this kind of stuff is the scalar. So they cannot give the vector. Like you have axis. And so that's what I don't believe many people doing that. I just say, I'm just curious. This sounds to me, is the universal nature. That's everywhere. That means they pairing, as I say, rotated, pairing, merging one axis. That's something like that. Yeah, that's what usual. It is looks like sounds to me about similar, just like MVG, like other. You did the MVG as well. You know that it is also similar to that. Even they do the turbulence for formulation. The reason I think is very simple, because the shear must be changed to Nutex. If you don't have Nutex, you don't have turbulence. Anyway, you don't have vortex. So that's the only way. That's the only way the shear becomes rotation. That's what I say. Then turbulence.
Yes. I believe the Liutex core-line method can give us some ideas to study the droplet escalation.
Yeah, that's nice. Yeah, you talk about the multi-phase flow and the drop. Yeah, that's nice. Thank you.
Thank you, Professor Liu. Okay.
Is there any other questions? Okay, if no questions, let's do a 10 minutes break. Okay, so see you in 10 minutes.
Thank you, Yifei.
Thank you, Dr. Dong.
Charles? No, yeah.
Hi, Dr. Liu. What's up?
Yeah, I'm just curious. Oscar is here? Yeah.
Yeah, Oscar's here.
Oh, he's here. Okay. I just want to make sure that he doesn't miss the talk. Yeah. So, so next session, right? Okay.
Yeah, I'm here.
Okay.
Yeah, Oscar's here.
Okay. Good. Okay. Good. I just want to make sure you're here.
Good morning, everyone. Session 2 will begin in about 1 minute. So I'll give everybody 1 minute to, reach back from the 10-minute break. And I'll be the host for this isn't session 2, session 6, actually. This is the second session for today, but it's session 6. The original host isn't able to make it, so I'm standing in place of him. My name is Charles Nottage. I hosted session 3 yesterday. The first speaker will be Yinlin Dong, Dr. Yinlin Dong. And yeah, so I'll say some more in about a minute. Okay, Dr. Yinlin Dong's topic for today is rules of tensor and matrix operation for Leotex calculation. Dr. Dong?
Okay, yeah, thank you, Charles. I'll share my screen.
Yes, you can. Go ahead.
Okay, hi, good morning, good afternoon, good evening, everyone. I'm Dr. Yinlin Dong from University of Central Arkansas, United States. And today my topic is rules of tensor and the matrix operation for Liutex calculation. And this is a joint work with Yifei Yu from University of Texas at Arlington. So in this presentation, you are now to see some physics, any graphics or any simulations. So instead, let's do some mathematics. So let's get started. So as we know, tensor is of significant importance in mathematics as it can be used to describe many important physical features, such as velocity gradient tensor and the stress tensor. The original math definition of tensor is based on the summation of unit delegates, which results in a difficulty of tensor operation. So in practice, the people usually express tensors in the format of matrices for the second order tensor. Therefore, the operation of tensor is equivalent to the operation of matrices, so which is much more convenient. Right? However, it seems that there is not an agreement on the relationship of vector tensor and the matrix, as well as tensor operation and the matrix operations. So one argument is whether to use array matrix or column matrix to represent a vector. So array matrix like the row matrix. It does not raise much confusion to express a vector by a matrix, as people can recognize a vector easily, whatever it is expressed by an array or by a column matrix. But a disagreement occurs when expressing a tensor. For example, I take the velocity gradient tensor. We just call this del V as an example. So there are two widely used matrix forms of the velocity gradient tensor. So one is partial u, partial x, partial u, partial y, partial z, partial u, partial z. So this is on the first row. Then the other is the transpose of this, the partial u, partial x, partial u, partial y, partial u, partial z on the first column. But if we have two matrix forms, so the inner product of del v dot u so would lead to two different results. So to make sure the matrix and the matrix operations are properly used to present a vector, tensor, and their operations, it is necessary to reach an agreement, including the ways to express vector tensor by matrices, the matrix operations, and the tensor operations. Right? So this is the motivation of this paper. As we know, Vortex is an important element in fluid dynamics. People used to believe Verticity is an indicator of Vortex. However, many experiments and simulations have shown that it's just an approximation where the shear is small. And Lyotex is an emerging concept recently posed by Dr. Liu, which represents rigid body rotation of fluid. The magnitude of Lyotex reflects twice angular speed, and the direction of Lyotex is the swirling axis. Dr. Liu and his collaborator are working on improving Navier-Stokes equations with matrix expressions tensor and have achieved some initial results. So now let's see some expression of vector tensor by matrix. First, column matrices are used to represent the vectors. So definition one, matrix form of a vector is U, is like a column, right? A column form. And since a tensor can be expressed by the outer product of two vectors, we define the matrix form of outer product first. So which leads to definition two. Right? Suppose we have two vectors. The matrix form of outer product of U and V is the following, right? Is U times V transpose, so which ends up with U1, V1, U1, V2, and so on. And in definition three, we define the matrix form of a second order tensor, Aij. Right? So which actually is the same matrix as the last page, right? The same as the outer product of UV. but it's still the definition of the second order tensor. It's like a matrix U1, V1, U1, V2, and so on. And now let's let UV be two vectors and Aij, Bij be two second order tensors, where Einstein notation is used. Big U, big V, A and B are the corresponding matrix forms of vectors UV and the tensors AB according to definition 1 and 3. Then for the dot product of two vectors, we have the following equation 4. The U dot V equals Ui Ei dot Vj Ej, and since Ij should be the same, right? So the summation Ui Vi, so which is just U transpose V, so as regular as before. And next, if we use vector U dot tensor Aij, the operation is as follows: equals Ui Ei then dot Ajk Ej Ek. And here, since Ij are the same, so we replace J by I. Then we write this down. So this is the vector on the second row. And then this vector can be written as the product of a matrix A and vector U. Is A transpose, actually it's A transpose U. We can also write it as U transpose A T, right? Transpose, right? UTA T. Then if we use a vector to write the dot product of the tensor Aij, so the operation is as follows. Right? So here Jk are the same. Right? So we replace K by J. Right? So we have the following summation, and this summation equals matrix A times a vector U, or matrix U, right? Matrix form of the vector. So it's just AU, right? It's just AU. Then finally, if we have the dot product of two tensors, Aij and Bij, equals Aij, Eij, Bm, and Em, En, and here J and M are the same. Right? And we end up with this long equation, and it turns out to be just the product of two matrices, AB. Right? So tensor A dot tensor B equals the matrix A times matrix B. Okay, to sum up, so we have the following rules for the vector tensor operation. The first, dot product of two vectors equals U transpose V. Second, and the vector dot product left dot product tensor A equals UTAT. So equation 9 will be used in later. And then Aij tensor dot vector U is just equals AU, and tensor A dot tensor B just equals AB. So this is just in the same order, only equation 9. So it's a little different. Okay. So next, let's look at the matrix form of velocity gradient tensor. So people use gradient or del F to denote the gradient of a function F. Following this notation, del V is widely used to denote the velocity gradient tensor. And according to definition 2, the del V, so which is the inner product, the outer product of these two vectors, right? Like the first vector is like the operator. So we write this out. So that's in equation 12. So partial U, partial X, partial U, partial Y, and partial U, partial Z. This is on the first column. So this should be the form of del V, but in some other textbook, gradient V is equivalent to the transpose of this matrix. So which one is correct? We can also check it from physics. Right? In physics, the velocity increment dv, which is like the total differential. Right? So along some direction dr can be evaluated by the inner product of gradient v and dr, and that is dv equals dr dot gradient v. Right? So here dr is on the left. Right? By equation 9. Right? And we have a vector dot a tensor, right? So equals the transpose of this vector, then the tensor, and transpose UTAT. So the transpose of dr is a column, right? dx, dy, dz, right? Then dot v, and then it equals the total differential, so which is dv. So that means the gradient, the velocity gradient should be del v. Right? So this matrix form, so is appropriate. Right? Is appropriate in equation 12. Okay, so here we want to make two remarks. First, we are not saying it is wrong to use the transpose of del v to represent the gradient tensor, the velocity gradient tensor. We just say that the transpose of del v is now the gradient v under equation 13. This definition 13 is from physics. But if in some other textbooks, if they define the dv as gradient v right down the dr, and then the transpose of del v becomes the correct way to represent the velocity gradient tensor. As long as the definitions are consistent, and that is fine. Then second is not the only matrix form to represent the vector tensor for their operations. As long as all the definitions are adjusted correspondingly, an array matrix can also be used to represent a vector. So now let's look at some explanation of the source of stress. And there is a misunderstanding that the stress is produced by symmetric strain only in fluid dynamics. The classic NS equation is as follows. That is equation 15. So which indicates the last term, symmetric tensor, the del v plus del v transpose, contributes to the stress. So while the anti-symmetric tensor del v minus del v transpose does not, since we cannot see this term in this equation. However, let's talk about the decomposition of del v in Koji Stokes decomposition. Del v can be decomposed into two parts, symmetric part and the anti-symmetric part. If mu is the viscosity coefficient, then the stress tensor F can be written as the summation of these two, and also the divergence of F is as follows: is the summation of the symmetric tensor and the anti-symmetric tensor part. For the incompressible flow, so we have the gradient of the transpose of del v equals 0 vector y, because the divergence, that's the gradient operator dot the transpose of gradient v equals the following. That's still by the equation 9 equals utat, the transpose of the operator, then times del v transpose, which is partial u, partial x, partial u, partial y, partial u, partial z on the first column, first row. So equals this Laplace, and then factor the operator out, the partial x, partial x, then the divergence of v. But for incompressible flow, the divergence of v is 0, so we obtain a 0 vector. Since this term is 0, then we have equation 20. So the symmetric part and the anti-symmetric part actually is the same. So that means they make the same contribution to the stress, and not only the symmetric part. And secondly, let's look at how about for the compressible flow. So we derived a new form of the NS equation. In the previous slides, we have shown the divergence of the transpose of del v is the follows, but for the compressible flow, this equals del and then divergence of v. So these two terms in equation 21, these two terms are the same. So we can rewrite equation 15, the original NS equation, as the follows. So let's go back to equation 15. This one is like in the last term, we minus twice of the transpose of divergence del v, and then plus it to the previous term. So if the coefficients of the second last term becomes 4/3, 4/3, then we have a negative sign in the end in equation 22. So you can see the anti-symmetric tensor is there. So why we rewrite the NS equation? There are at least two advantages. First, the new form of NS equation reduces the number of unknown variables because the symmetric tensor in the classic NS equation has 6 unknown variables. So while the anti-symmetric tensor only has 3 unknown variables. So because the diagonal elements are all zeros. So this will much reduce the computational cost. Then secondly, the anti-symmetric tensor del V minus del V transpose is Galilean invariant, which means the results keep the same under different coordinates. Okay, let's make some conclusion. First, for a long time, the use of matrices to represent the vector, tensor, and their operations is not consistent. In this paper, some operational rules are established to eliminate any confusion. So in the future, if we look at the papers about Liutex, at least we can get some agreement about the notations. And secondly, for the incompressible flow, we have shown that the symmetric tensor and the anti-symmetric tensor make the same contribution to the stress tensor in the NS equation. Then for the compressible flow, we introduce a new form of NS equation. So we can see that the computational cost will be much reduced. Yeah, thank you. Yeah. So that's my presentation. Thank you for your attending.
Thank you, Dr. Wong. I mean, Dr. Dong. Sorry. Any questions for him? Okay, so Dr. Dong, you could stop sharing your screen. Yeah. Our next speaker will be Oscar Alvarez. He hails from University of Texas at Arlington in the US, and his topic is Leotech core tube for Vortex visualization and structure. Oscar?
Okay, let me share my screen.
Yes, go ahead.
Okay.
You need to put it in full screen mode.
Yeah. Okay. Hello, my name is Oscar Alvarez, and I'm from the University of Texas at Arlington. I'm a student under Dr. Chakum Liu, studying Leotex, and today I'll be talking about the Leotex core tube for Vortex visualization and structure. Here's the outline of the presentation. So when we talk about vortexes, we're talking about the rotational or swirling motion of fluids. We all know that vortical structures are a constituent part of turbulence. And lately they've had, or since of recent, they've had the problem of not having a rigorous mathematical definition, but Leotech seems to be closing in on that gap. So we all know of Liutex. It's a new recent third generation Vortex identification method found by Dr. Chakum Liu. It was previously known as Vortex, but renamed to be Leotex. This method is not affected by the problems of previous generations of Vortex identification methods. Leotex is a systematical definition of local fluid rotation, and it has scalar, vector, and tensor interpretations of the local fluid rotation. So we all know the strengths of Leotex. We know that Leotex is vector-based, and it's going to help us define the core size and core center of a vortex structure. Here's like a short synopsis of what Leotex is. We know that the Leotex vector bold R here is made up of unbold R, which is the Leotex magnitude, and then little bold R, which is the direction of the Leotex vector. So the data I'll be using for the rest of the presentation is direct numerical simulation of the flat plate boundary layer in the earlier transition phase. And for the rest of the figures, we'll be focusing more on this area around the 420 mark, just for the rest of the presentation. So to find the Liutex core tube, we're going to need to borrow some things from when you build the Leotex core line. So one of the most important things that we need to use is the Leotech, the gradient of the Leotex magnitude. So this is the gradient of Leotex magnitude. We're going to integrate this vector over our known vortex structure. And when we do that, we create stream traces. And these stream traces converge to the center of the known vortex structure. So here we have the iso surface of Leotech magnitude, which is our known vortex structure. And when I create stream traces with the components of the gradient of Leotech magnitude, you can see that they all converge to a local max point. We could say that they're all converging to the rotation axis of the vortex. When we're creating this, the Leotex core line here, we look for when the Leotex line is parallel to the gradient. And when we do, we have this nice center line without all the protrusions of the gradient. And when we add the contour of the Leotex magnitude, or we add the color, we create a Leotex line, and we have the gradients, or we have the Leotex core line. So this is a segment of the Leotex core line, and you can see that it goes throughout the center of our vortex structure, and it gives us a lot of information. We could see the Leotex magnitude changing and stuff like that. Well, to build the Leotex core tube, we first need to select strength or size of the core tube. So this is just an arbitrary percentage. So I can choose to be 95 or 80 or 99%. And it's going to be 99 or 95% of the local max seed point. So the local max point that we chose to create the Leotex core line. After that, we'll draw an iso surface of the Leotex magnitude at the selected percentage of the local max value. Then we'll create Leotex lines at the intersection of a plane intersecting the local max point and the iso surface. This is a lot, but I'm going to go over this in the next few slides. So here is the local max point that we use to generate the Leotex line. And I'm now defining my Leotex tube size. So I'm saying I'm gonna just choose a size for the purpose of this presentation to be 95%. So the Leotex magnitude at this local max point was this value right here. So to get the the value that I want, I'm gonna take 95% of that value. And this new value is going to be the 95% strength of this local max point here. After I have this new Leotex magnitude, I'm going to create an iso surface and of this value. And what you see here is that this plane that we use to intersect our local max point here, this red dot, comes in handy because it also intersects the iso surface that we create at that 95%. Now, the next thing we're going to do is we're going to use the Leotex vector, and we're going to use the components of the Leotex vector, and we're going to integrate it. And we're going to get Leotex, these streamlines using the Leotex vector. And I'm going to make these streamlines at the intersection of the plane and the iso surface that I just made. So I'm going to go around this entire intersection, and I'm going around this entire intersection. And I apply a contour. So we apply the color of the Leotex magnitude on all the stream traces. And when we do, we get our segment of the Leotex core tube. So it was around this area where my mouse is that we created the core tube using that red dot, the seed point, and the local max point, and it created this entire vortex structure here. You can see that there's a lot of information, being provided just from using just one seed point. We have, you can see different colors, which represent different Lyotex magnitudes throughout the structure. We can see some of the known vortex structure, just such as the legs here and the hairpin here. But also more importantly, which we'll see in the next slide, the features that appear here that aren't in the isosurface. So using the Lyotex magnitude at 95%. So if this is the vortex tube generated at 95%, this is just the Lyotex isosurface, so just the magnitude isosurface. And we're only looking at the region to the right here of this black line. And what we can see is just the contrast of features that are missing in the Lyotex magnitude isosurface that are present in the Lyotex core tube. So here in the isosurface, we're missing large regions of the legs and the connective regions between the hairpin and the legs, where in the Lyotex core tube, we can see clearly that they're definitely connected and they're all part of the same structure. And we're also missing a lot of information connecting the two legs. So here in the connective region between the two legs, we have almost two different vortical structures, and it's not shown in the Lyotex magnitude at 95%. We're missing a lot of this information. Another thing to notice is that the isosurface is only one color. Since the isosurface is only one color, we can only see one threshold value. So we would, if we compare it to the Lyotex core tube, which shows multiple threshold values, that means we would have to have multiple instances of the Lyotex isosurface to represent a similar vortex structure from the isosurface comparing to the Lyotex core tube, so to represent multiple Lyotex magnitudes. One thing that we have to understand is that the isosurface is always a part of the Lyotex core tube, right? We use the Lyotex isosurface to create the Lyotex core tube, but the Lyotex core tube is not an isosurface. So it's not an isosurface, it's vector-based. You could see the change in threshold and all that good stuff in the Lyotex core tube that you can't see in the isosurface. We also see that the Lyotex core tube exists almost everywhere where we don't have an isosurface. So we saw that we saw that we had areas with no vortex structure in the isosurface where we did have in the Lyotex core tube. So we're going to be comparing the Lyotex core tube with the really popular Q method. Q method is currently the most popular method used around the world for vortex identification. The Q method is sensitive to threshold. So again, it's an isosurface. So you don't really know what the actual vortex structure is. You just have to kind of pick whatever you feel is the right structure threshold. Q method is also scalar, and this is very, very important because we created the Lyotex core tube using the Lyotex vector. So we needed a vector to create the core tube. And since the Q method is scalar, there is no possible way we could create a core tube like we created the Lyotex core tube. So we cannot create a core tube using the Q method even if we wanted to. At least in the same way we created the Lyotex magnitude core tube, or the Lyotex core tube. So here's on the left is Lyotex core tube that we just created, or the segment of the core tube. And then if we look to the right of the black line, we see that this is the Q method using this isosurface, the Q isosurface using this Q value. And we can see again the same problem that we had with the isosurface of the Lyotex magnitude, where we have a lot of missing structure here connecting the legs and the hairpin. And we're also missing a lot of structure here in the center between the two legs. So this is running in the same issue. It feels like this is an isosurface between the isosurface issue between the core tube and the isosurface is that we're missing a lot of connective air regions of our known vortex structures. Again, we see that the Q method is only one color. So the Q method can only represent one scalar threshold value at a time. So if you wanted to compose similar situation as the core tube where we have multiple thresholds shown at simultaneously, we would need multiple instances of the Q method shown overlapping, which can get really messy. So why not just change the threshold? Well, here's the threshold again. You can see it's a lot, they're getting closer and closer together. It's getting more clear and more similar to the shape that we have here on the left with the core tube. But again, we're missing this giant structure between the legs that's not appearing in the isosurface. We would not notice this in the isosurface. We'd probably have to guess that this exists, but in the Lyotex core tube, it's quite clear that this is part of the vortex structure. It connects the legs here all the way to this other leg, and all the way up to this little hairpin up here. So there is vortex structure that exists here that is not being displayed using the Q method isosurface. So in conclusion, thanks to the vector-based Lyotex, we can find the vector-based vortex tube. The Lyotex core tube is a new technique, and I think it's a fantastic way to identify vortical structures. And we're currently developing an algorithm, or planning to develop an algorithm to automate the process of finding the Lyotex core tube. And this is just a picture that I took that looked really cool when I was drawing all that stuff. Thank you, and if there are any questions.
Excuse me, can I ask a question?
Yes, go ahead.
Yeah.
Yeah, my name is Hong Yisu. It's a very interesting topic. Actually, when you plotting the core lines there, and you define the boundary based on 95%.
Yeah.
Can you show me how many grid point from the core line to that outside the boundary? You mean, I mean the vortex cube boundaries.
The vortex.
How many? Yeah, the grid point. You have the DNS results there, right?
This one right here, right?
Yeah, yeah. The grid point inside your tube. How many grid point there?
Oh, I'm not too sure. So this is a smaller subset of the entire data structure. So this is
I know. Yeah, we also try to do this, but we find for the DNS results, we cannot find enough point to define these boundaries based on the DNS data, the grid point there. So therefore we have actually that the shape of that cube is really not the real shape if your grid point is refined enough. Do you know what I mean? I mean, you have to check whether there are sufficient number of grid points to represent that tube boundaries.
Are you saying the dimension of my data set needs to be sufficiently large for this to work?
No. I'm not mean you have to. I mean the grid point try to resolve these vortex structures. So that's the tube structure, right? You try to use that tube structure to represent this vortex structure, right? I mean, the grid point content within that tube. Did you check how many grid points inside your tube?
Oh, inside my tube. So how many grid points are in here?
The grid point, yeah. That's how many grid points inside this tube.
Oh, I haven't checked. Are you asking about how many of these did I plot, or how many data points?
No, not how many you plot. I know how many. I can count how many you plot, but can you check how many grid points inside these cross sections?
I guess you could. Right now we're working on finding.
Yeah, but we find that the grid point inside these structures are very small. So it's hard to say these geometric structures is really the real one, because if we refine the grid point there, the shape definitely will change.
Yeah, so it's very, this Vortex, the Leotex core tube, is extremely dependent on where you place your seed.
Yes, that's the point. I mean, your results is really grid dependent.
I see.
Right?
Yeah. Where it depends wherever we put the seed point. So I just chose somewhere in the legs. Yeah. So I just chose it. I did it by hand, and it gave.
Let me explain a little bit. I think you're right. It depends. That's empirical, really empirical. Yeah, depends what's the definition for the tube. So I think the core line pretty much important. That's the unique.
Yes,
the core line, the core.
I agree.
Yeah, but the tube, it is really empirical. What is a tube? How big is the tube? Yeah, so the situation you mentioned, that's be true. Really, how many points you pick? So that's pretty much. I told Oscar quite many times. I just said more important is the core line. That's the one thing. Yeah, it is important because that could be unique, but no matter, you don't need a counterpoint. But then beyond the corner, you want to find a tube. This is man-made, really. It's not you have the very unique definition. I think it is almost impossible.
Professor, I believe eventually, I mean, if you have, suppose if we have a very refined DNS data where it is the results can make it grid independent, then you will have the right geometry of Vortex.
Yeah, but you still need to define 90%, 95%, 99%. Yeah.
That's the boundary where you have to define. But within that boundary, you have to have sufficient grid
points. Yeah, I agree.
To resolve that, to represent that shape, to make that shape accurate,
I agree.
sufficient accurate one.
Yes, I agree with
your structure will be grid dependent.
Right. That's
so
correct.
At the end, because DNS results supposed to be grid independent, right? If
Yes.
ideally, right?
Yes.
So
Yes.
yeah, that's my point. So the having that said, I would say right now you can try
Yes.
this method to give a roughly a structure, but really
Yeah, it's
it
still
is
working.
not.
So which institute you're from? Yeah.
Mhm.
No,
Pardon
I
me?
ask you. Yeah, which university? I don't know your name and
Oh,
institute.
my name is Hong Yi Su. I'm from Fudan University.
Oh, for that. Oh, okay. Yeah.
Oh,
Okay.
my name
I
is
know
Hong
that.
Yi Su.
Oh yeah.
You see my name there?
Yeah. So yeah, no, because you didn't shoot. Yeah, that's I agree with that. Well, but well, he really raised a very serious question. What is a serious question? We just say if the isosurface is vortex structure or not.
No,
So
definitely
this
not.
is
I know,
serious. Yeah.
we all know, but the question we're asking here is whether this tube is
Yes.
a true vertical structure.
Yeah. I agree.
Right?
Yeah, I agree.
We all know isosurface is not. That's for sure.
Yeah, no, maybe not. Yeah, that's serious because everybody use isosurface. Everybody. So this is really serious. Yeah. Unfortunately, you know, we before Oscar, that's the other student working on this area, but now he's a continue, yeah, to do her work. I think still in the process. So yeah, his results is not final. Yeah, I agree. Yeah, depends on how many grades. Yeah, depends on your definition, but the core line is unique. Yeah. More important, I think.
Okay.
Thank you for the questions for Oscar and also the input from the doctor from Fudan University. And in the interest of time, we have to move on to the next speaker.
Okay.
So Oscar, you could stop sharing your screen.
Thank you.
All right, thank you.
All right, thank you. Yeah. So the third speaker for the session 6 is Qinqin Zhao from Fudan University, China. And their title is Aerodynamic Interaction Study Between NACA 0012 Airfoils in Tandem. Zhao, Dr. Zhao.
Yeah, can you hear me and can you see the screen I shared?
Yeah, we can hear you and we can see the screen. Yeah. You could just put it in present mode. Yeah.
Hello, ladies and gentlemen. I'm Qinqin Zhao, a postgraduate student from Fudan University. Today, I'm glad to talk about my research work named Investigation of Aerodynamic Interactions Between NACA 0012 Airfoils in Tandem. Flow-path airfoil is a well-known topic in central research in fluid dynamics. No matter in the research of the natural phenomena about bird flight or in the modern aviation industry of aircraft manufacturing. So studying it and their aerodynamic interactions is quite essential and significant, especially understanding the lift, drag forces, and the momentum of wings. In our work, we use high-fidelity direct numerical simulation database in order to get more accurate results and discover more flow details. And we use the third-generation Vertex identification of Liutex approach as a visualization method because we think it can identify the local rotation of fluid motions. The model we use is dual airfoils in tandem with two NACA 0012 airfoils, and the computational domain is shown in this picture. The DNS data were generated by two-dimensional incompressible unsteady Navier-Stokes equations. The Rayleigh number was set to 10,000 with the chord of airfoil being the characteristic length and the free stream velocity being the characteristic velocity. And the attack angle of both airfoils equals to 4 degrees. Besides, the boundary conditions were also shown in this figure. The left side is the uniform inlet flow, the Cartesian components of velocity, at U equals to 1 and V equals to 0. The upper and lower side are far field boundary. The right side is the downstream outlet flow, and the wall boundary was set to the non-slip condition, and the initial conditions were set as a uniform free-stream velocity field. In the past, the configuration of airfoils was investigated by experiments of the wind-tunnel test, but it's often costly. And as the development of computer and computational techniques, some numerical methods like RANS, LES were created as important techniques to get the flow information. But these methods have errors due to their inherent hypotheses, such as traditional turbulence closures like eddy viscosity hypotheses. So using this data sometimes couldn't investigate accurately and precisely. But with the availability of power computing and strong data storage capacity, DNS is accessible to researchers. Therefore, more accurate data can be used for the detailed research, flow research. The DNS data we use in our research come from this website. This is the DNS database at Fudan University. Besides, the visualization approach in our research is a third-generation Vortex identification method. The traditional method was based on Verticity, the curve of the velocity, but it can distinguish between a shear near region and a real rotational region, such as at the near wall region in the simple shear flow. Vertex is a natural phenomenon, but verticity is a mathematical definition. There are two different concepts. Since 2014, the new vertex identification method has been developed by Dr. Liu's team at UTA to address the shortcomings of the former traditional methods. The major idea of Lyotex is to extract the rigid rotation part from fluid motion to represent vertex. It may open a new door for turbulence research. And the flow visualization of the DNS results in different methods are shown there. The top one is visualized by the first generation vertex identification method based on verticity, and you can look at the flow field. Like I said before, vertex is not verticity, and you could see the verticity is also correlated with the shearing motions represented by shear vector. By comparison, the bottom one has the evident differences. It's displaced by the Lyotex vector, which is extracted from the verticity to represent the rotational region. From this picture, you can clearly identify the vertex pattern and the cones representing the Lyotex normal maximums and minimums, instead of mixing them in the verticity shown on the top. And you could observe and compare by the two videos. According to the high fidelity data and new visualization method, we could analyze the flow details of airfoils in tandem. Firstly, we could study the airfoil forces and their relations of both airfoils, including lift, pressure drag, and viscous drag. The three figures on the right present the aerodynamic coefficients of the front and back airfoils with the horizontal axis. The black line represents the results of the front airfoil, and the red line represents the back one. And the curve means the variation on time, and the straight line is the average coefficients when fully developed. From the three figures, it's evident that the lift coefficient of the back airfoil is larger than the front one, and the drag coefficients of the back one are smaller than the front one, no matter for the pressure drag or the viscous drag. And the lift drag ratio of the front airfoil is 3.54, and the back one is 4.75, which is larger than the former one. And the results can be validated by the data from former RANS data. Comparing the aerodynamic coefficients of the two airfoils, it's shown that the back airfoil owns an evident aerodynamic advantage over the leading one. The lift of the back airfoils increased by 13.7%, and the pressure drag reduced by 14.7%, and the viscous drag decreased more, which is 19.1%. This provides a reasonable explanation for the formation flight that most birds choose to take, since the birds in back row can take advantage over the front bird to obtain an increased lift and reduced drag, which is also consistent with the report from Nature that it sees the enrich consumption of 11.4% to 40% in the long-distance flight of pelicans in Vortex weeks. After analyzing the mean aerodynamic coefficients, we study the frequency spectra of these coefficients by fast Fourier transform. The frequency spectra results are shown on the right. The front airfoil is shown on the left column and the back one is shown on the right column. We could see that the leading airfoil has 2 harmonics and the rear one has 3. And for both the front and rear airfoils, the spectra of all coefficients demonstrate a major characteristic harmonic at the frequency of about 2.21 or the period about 0.45, which can be explained easily by the visualization of Liutex that the periodical shading of the vertices from the trailing edge of both airfoils is the major source inducing the major frequency. Moreover, the subharmonic with frequency about 4.42 is found at the back airfoil, which reflects the aerodynamic interactions between the 2 airfoils. Then, we investigate the vertex characteristics and airfoil vertex interaction mechanisms from the visualization of Liutex. This clip shows the associated pattern of vertices and their interactions around the front and back airfoils. We can see that a passageway formed by a 2-line vertex structure on the upper and lower surface of the back airfoil. The outer vertex row from the leading airfoil takes the form of vertex pair and makes the back airfoil located in the vertex pair corridor. It makes the inner rotating vertices shading in front of the trailing edge on the upper surface at the major frequency. This can be demonstrated by these figures. Figures on the top are the variation of shading vertices at the trailing edge of the front airfoil, and on the bottom, it shows the variation of vertices generated and migrated on the upper and lower surface of the back airfoils. We can see that the flow of the shading vertices remains the same after the same period time. This is also explained that both of the airfoils share the same major frequency of the aerodynamic coefficients, and the variations of vertices have the impact on the aerodynamic coefficients. And by analyzing the vertex pair impacts, the subharmonic of the rear airfoil in the aerodynamic coefficients can be explained by these figures. While the vertex pair passes the leading part of the back airfoil, the starting of a cycle is selected when the rotating center of the front vertex coincidences with the vertex tangent line on the upper side of the leading edge of the back airfoil. Then it can find that after a period of T1, the next front vertex rotation center passes the vertex line on the lower side. And this period is identical to the sub-frequency harmonic in the coefficients of the back airfoil. So it means that the subharmonic of the back airfoil is from the vertices of the leading one, which periodically influence the flow on the back airfoil. Next, we investigate the physical mechanisms of the fluctuations of various aerodynamic coefficients. The surface pressure and Rotex control distribution of the front airfoil at 5 typical moments are calculated based on the DS data and presented on the left. And the variation of the coefficients in one cycle when fully developed are shown on the right. For the point A and E, the lift and pressure drag reaches their maximums and the viscous drag reaches its minimum. This is because that the low pressure region dominates the upper surface. For the point C, the lift and pressure drag reaches minimums and the viscous drag reaches maximum. This is because 80% low pressure region on the lower surface that leads to the minimum value of lift. For the Rotex contour distribution, the vertex size increases and the low pressure region of upper surface increases accordingly, and low pressure region of upper surface shrinks quickly due to the vertex migration or shading. The correlation gives a clear explanation for the fluctuation of the lift coefficient. Similarly, the left figure shows the surface pressure and Rotex contour distribution of the back airfoil at different typical moments, and the right is the variation of aerodynamic coefficients in one cycle at different moments. Compared to the front airfoil, the variations of back airfoil are more complicated, especially for the pressure drag. It has 7 typical moments due to the subharmonics interfered by the vertex pair from the leading airfoil, but it's also identical to the leading one that the distribution of pressure leads to the variation of lift. Moreover, we could find from the contour that the vertex core area is likely accompanied by a local no pressure region. In the end, I summarize our research work shortly. In our work, we used DNS data and the third generation vertex identification method of Liutex to analyze the airfoil vertex interaction mechanism of airfoils in tandem. The results show that the trailing airfoils gains an obvious aerodynamic advantage over the leading one with an increased lift and a reduced drag, which makes the bird flight more energy efficient. And due to the leading airfoil weak, a vertex pair passageway structure is found to play an important role in the aerodynamic interactions with the front airfoil. It could explain that the major harmonic and subharmonic in the aerodynamic coefficients. Then we analyze the surface pressure and Rotex contour distribution of two airfoils, which are consistent with the variation pattern of the lift coefficient. Thanks for your attendance.
Thank you for that talk. Interesting topic. Does anybody have any questions for Dr. Zhao?
Well, yeah.
Do you hear me?
Yeah, first, it's like a very interesting work. It sounds to me, you say that the two aircraft, or you two airfoil really. The second one, third one get a benefit from the first one. Sounds to me you get a less drag or something like that. That's interesting. Yeah, I think this maybe people already know this, but it's not that clear. And the second thing is the first one is sounds to me you don't have separation. You have shear. I see the shear. I didn't see any sounds to me you only have wakes. You don't have separation on the ring. So well, that depends on your angle. I think your attack angle. If your attack angle is larger, that could happen. So right now your attack angle is almost zero. Is zero or is you have some attack angle? I didn't find it. So you understand my question? Do you have attack angle for these rings, or you don't have?
The angles of attack of both airfoils was set to 4 degrees.
Oh, 4 degrees.
It's not large, so maybe
Okay.
you can
It's not
find
zero.
the separation. Yeah.
Everybody have 4 degrees, right? Everybody.
Yeah.
But the different, the physics is different. First one doesn't have any separation. Sounds to me, you have separation, not vortex. But the second one, third one, you have. But you only have second one. But it sounds to me, your second one is induced by first one, right? They have vortex, shading. but the vortex shedding frequencies is induced by first one. Sounds to me. What you call a harmonic or subharmonic. And that's interesting. That's interesting, but not by itself. It's by the first one. If they, independently fly, it may be different. That's correct. My understanding is correct. Yeah. But the third one, it sounds to me, if we use vorticity, you get both. You get the shear and the rotation. They're mixed. It's not clear. It sounds to me like a first airfoil is clean. For the Liutex, it's clean. Not for the Vertice is not clean because they share. They share. Yeah, look at the Liutex is very clean. The Vortex shedding is very clean. Yeah, they mix. Vertice is mixed, I think. But the good things is, I say, it sounds to me, the second airfoil, the Vortex shedding is determined by first. Really, I think this could be, depends on the distance as well. I think it cannot be the same frequencies. I don't know. Yeah, I didn't decide.
Professor Liu,
yes.
Let me explain it a little bit. It's very interesting here. As you can see, in the for the upper one, we use vorticity, right? And you see a lot of shear effect there.
Right.
Definitely, the vortex, the weak shedding happens at the trailing edge of the first airfoil, right?
Right.
You can see it only happened at the trailing edge. But for the second airfoil, this trailing edge, still there is a vortex passing that trailing edge. But really, this vortex generated where upstream up to the almost the 1/4 of the chord length.
Right.
So in our opinion, is the airfoil interactions really cause this shear layer being broken and move upstream. Actually, they are the same vortex, but it's just the move upward, move upstreams. So that, and we checked this the vortex shedding, the major frequency is the same as the first one. Therefore, the vortex near the surface is really shedding at the same frequency. Although there are 4 vortex, but they are the shedding frequency, the major shedding frequency is the same as the leading edge one. But the second subharmonics is appearing on the second one, on the trailing airfoils. But for the first leading airfoils, there's no subharmonics. So it's very interesting. I mean, here it looks like we have a major frequency for this airfoil. Whether it's the leading or trailing, they are the same.
Yes.
But for the second,
that's the measure, frequencies. Yeah,
it's kind of
determined by the
intriguing.
By the airfoil shape. Yes.
Yeah. So
sorry,
the interaction really caused the vortex being generated more early than the leading airfoil.
Yes. Excuse me, professors. Sorry to disturb you. This is very interesting and all, but we have to move on to the next.
I understand
speaker.
more. Yeah.
Okay.
Okay.
Thank you, Dr. Zhao.
I have a question.
Do
you hear me? I'm Yu Xianxia, Shanghai Institute of Technology. I have a question. Your result is interesting, and what reason is the formation with a single point or test point near the airfoil. Actually, I think the vortex pairs does not direct in action with the surface of the airfoils. What the reason is the formation of the single vortex point. Do you hear me?
Single. Excuse me, I'm not quite understanding you. Maybe you're talking about the vortex generation on the second one or the first one? On the trading or the
second one.
On the second one. So the second one, as you can see here, you can see there's a little bit blue, a green point there on the surface, right? That's the generation point. As you can see,
green point.
Yes, it is generated by the upper red vortex. Actually, it is a pair, right? There's a red one and a green one, and it always being generated by the red one. And when the red one passes this point, it causes the generation of a vortex on the surface. You see, there's an outside passageway, right? A vortex pair passageway, but the inner vortex is rotating in only in one direction. As you can see, they are all in the same colors, right?
Yeah. I got it. Thank
you. So it is caused by the outside vortex passageway.
Yes. So we need to move on to the next speaker. Thank you all for the questions. Can you stop sharing the screen, please? Our next speaker is Weibao Zhang from Beihang University, China. The topic is comparison of vortex identification methods based on the Lyotex decomposition and applications in aero engine compressor flows. Sal?
Okay.
Can you share your screen?
Could you hear me and see me?
I can hear you and see you, but you need to share the screen.
Okay, I'm going to share my screen. Okay, please wait a moment. Sorry.
Okay, we can see it. You can begin.
Okay, that works. Okay, let's begin. Hello, everyone. It's my great honor to be here to present our work. And I'm Zhong Weibo from Beihang University. And my topic today is a comparison of vortex identification methods based on the Liutex decomposition and applications in aero engine compressor flows. And the presentation contains 6 aspects. And first, we talk about the background briefly. And as we know, the vortices, As we know, the vortices are everywhere in nature and in engineering flow, and they are famously dissipated as sinuous and muscles of fluid motions. And the performance of compressor is notably restricted by complex vertical flows, such as the corner separation and the tip leakage flow. Thus, a deeper insight into vertical flows in compressor is of great meaning for exploring the flow mechanisms and improving the aerodynamic performance of compressors. But however, in vortex identification, vortices entangled with each other, and the vortex regions vary depending on the vortex identification methods by which they are extracted. And the comparison of different vortex criteria or identification methods and the research on their relationships are of importance. Okay, in the second part, we will briefly review the Liutex decomposition and the recently proposed local trace elliptical region indication method, and which is called the LTER method for short. Okay, for the Liutex method, in the transformed frame, it obtains the strength and the direction of rigid body rotation in swirling flow. And for the swirling flow, the discriminant, the delta, is positive, and there are complex eigenvalues. And the phi here is rigid body rotation strength, and we said the S1 is a shearing component along the rotation axis, the VR vector, and the S2, S3 are the shearing components in the rotation plane. And the real eigenvalue, lambda r, and the real part of the complex eigenvalue, lambda CR, they are compressing stretching factors. And the image part of the complex eigenvalue, lambda CI, is a well-known swirling strength, and which is related to the rigid body rotation and the shearing component S1. Okay, the Liutex-based velocity gradient decomposition provides an effective approach to distinguish the rigid body rotation, the pure shearing, and the compression stretching effects in the fluid motions. And the RS decomposition divides the vorticity vector into a rotation part and a shearing part. And then for the new local trace criterion, it constructs a new tensor, the psi, and which is half of the quadratic velocity gradient tensor. And the magnitude of the local trace criterion, the LT, is defined as the first invariant of the tensor psi. And the positive LT indicates a vortex region here. And the projection plane named as LT plane, as shown in the right figure, is constructed in the positive delta space. And its abscissa axis psi is a ratio between lambda r and lambda ci, and its ordinate axis eta is a ratio between lambda cr and lambda ci. And in the LT plane here, the projection of positive LT is an elliptical region. And incompressible flow with the P, the first invariant of the velocity gradient tensor, the P is equals to 0, is projected along a line across the original point. Okay, and as is known to all that in the positive delta space, the spiraling trajectory of the local flow point can be expressed in the curvilinear coordinate system, and whose basis vectors are the eigenvectors of velocity gradient tensor. The real eigenvalue of the lambda r reflects the stretching or compressing rate of the spiraling trajectory along the direction of VR. And the lambda cr indicates the amplification or damping of the orbital radius in the swirling plane, which is determined by the vector VCR and the VCI. And according to this, the coordinate axis and the P equals to 0 isoline, these three lines can divide the elliptical region into 6 parts, and each part has the corresponding spiral pattern, and they are summarized in this color table. And then the relationship of different vortex criteria can be expressed in details based on this series we mentioned above. And first, for the Q series criteria, the original second invariant Q contains the effects of compressing, stretching, and shearing. And the positive Q criterion is not a subset of positive delta space. And this relationship is shown by this Venn diagram. Okay. In the LT plane, as you can see, the positive Q region and the ellipse are tangential at point A and point B. And the point A and B are located in the P equals to 0 isoline. And for the commonly used Q criterion, it is the second invariant Q at incompressible condition. And according to its analytical expression, it filters the influence of compression stretching effect, but is still contaminated by the shearing component S1. And the projection of positive Q criterion Thank you, Charles.
Yes. Okay. All right. So we'll take the 10-minute break and then start session 7 afterwards. Thank you.
Hello, everyone. So our next session 7 will start. And the next presentation will be by Dr. Charles Yotex. So are you ready, Dr. Charles?
Yes, let me share my screen.
Okay, sure.
Oh, hold on 1 second. Unshare. How do I share? Stop sharing. I will be playing the video. You could tell me if you can hear it. Good morning, good evening, good night. Okay. Welcome to my talk. My topic is Statistical Analysis for Lyotex Growth and Flow Transition. My name is Charles Yotex, and here we go. What is a vortex? A vortex can be intuitively recognized as the rotational swirling motion of the fluids. This phenomenon brought about many years of research to classify and identify the vortical structure. Many vortex identification methods were developed and are categorized into 3 generations. First generation, which is Vorticity-based, the second generation, eigenvalue-based, and the third generation, Liutex-based or eigenvector-based. Prior to development of Lyotex by Leo et al. In 2017, there was no mathematical definition for vortex. First of all, what we're gonna do first is review the related vortex identification methods that we will discuss through this presentation. So to do that, we need to look at define the standard form of the velocity gradient tensor and show the traditional Koji Stokes decomposition. So this here is the standard form for the velocity gradient tensor, and it can be decomposed into A and B, A plus B, where A is the strain rate tensor and B is the vorticity tensor. Now vorticity, we're going to look at these 3 vorticity equations or formulas, right? So vorticity vector can be derived like this. The vorticity tensor is that B tensor that we saw before, and vorticity magnitude is derived like this. Now, Lyotex, on the other hand, is a vector defined as big R vector equals to big R times R small r vector. Big R represents the Lyotex magnitude defined as twice the angular velocity, and small r vector represents the directional vector of Lyotex. Small r vector is the real eigenvector of the velocity gradient tensor, and the explicit formula of R, big R, is as follows: omega vector dot r vector minus the square root of omega vector dot r vector all squared minus 4 times lambda ci squared. Now, the omega vector is vorticity, and the lambda ci is the imaginary part of the complex eigenvalue of the velocity gradient tensor. In computational fluid dynamics, many researchers and textbooks accepted that vorticity is vortex. However, this is a misunderstanding of the tensors derived from the Cauchy-Stokes decomposition of the velocity gradient tensor. It was believed that the symmetric tensor A and antisymmetric tensor B, which is the vorticity tensor, represented deformation and rotation respectively. The purpose of this presentation is to show, that vorticity is not entirely rotation. Secondly, to compare the behavior of vorticity to the behavior of Lyotex in boundary layer transition, and also to show the effects that shear has on vorticity. So firstly, we're going to look at vorticity is not entirely rotation. So to do that, I'm going to define a principal coordinate. So the principal coordinate is derived as so, as seen on the screen, where we start with the standard form of the velocity gradient tensor, and we let Q be an orthogonal matrix that rotates XYZ frame to big X, big Y, big Z frame, so that the big Z axis is parallel to the real eigenvector R of the velocity gradient tensor. So the transformation is as seen on the screen, this one here, where we have 0 and 0 here. Now we go even further and define a P, which is the rotation matrix around the fixed Z-axis. That's this matrix here. Rotating through theta around the Z-axis will give us the principal coordinates XY plane, as seen here. So this transformation. Now this is the one that we're going to use with these values here. It's very easy to find these out, figure these out. So this is where partial u, partial y is less than 0, and absolute value of partial u, partial y is less than or equal to absolute value of partial v over partial x. So this is the representation of the velocity gradient tensor that we'll use to prove or show that the vorticity is not just rotation. So next we're gonna, whilst we have this principal coordinate, the velocity gradient tensor and the principal coordinate, we will compute a principal decomposition. Now this decomposition decomposes this velocity gradient tensor into 3 parts: rotation part, shear part, and stretching or compression part. So that means that these values here are shearing components. These are the rotation components, and these are the stretching or compression components. This decomposition is unique and Gaussian invariant. Now, first one we're going to look at is the vorticity tensor in the principal coordinate. Now we can derive that using the principal coordinate velocity gradient tensor, which gives us this value for the vorticity tensor, and we could actually decompose this even further to get 2 other matrix. So from these matrices, you can see that this part is the rotation part. So vorticity tensor does, include the rotation part, and this matrix is the antisymmetric shear deformation part. So from this, we can tell that the vorticity is not strictly rotation, because of course it has shear. So next one we're going to look at is vorticity vector in the principal coordinate. So once we calculate that, we will get this vector here, and we can split that into 2 parts, which will give us a shear vector and a rotation vector. Now remember before when we did the principal decomposition, we found that these are the shearing components. So that means the vorticity vector includes shearing components and rotation components. So to go even deeper into it, we can actually do some more calculation to show that the vorticity vector is equal to a rotation vector and a shearing vector. So first we choose an arbitrary real vector, DC, which is this vector here. And we're going to multiply that by 2 times our vorticity tensor. So when we actually put them together and multiply them, we get to this vector here, and then we split it again, simplify it, and we get this cross product here. Now in this cross product, we have our DC, and we also have our representation of the vorticity vector. So that means that this is equal to minus DC cross product with the vorticity vector. As seen in the previous slides, we know that this B theta can be decomposed into a rotation part and a antisymmetric part, antisymmetric shear deformation. So we can do that here, and we can multiply with the vectors, and then we can work it out. So by working it out, we get these two vectors here, and then we can work it down a bit more, and we get these cross products. Now from this, we have DC and DC, and then we have R, which represents rotation, and these components, which are shear components. So we can represent them as R vector and S vector. And since we have two representations of this equation, they're going to be equal. So what does that mean? That means that these values, when we put them together, that means that the verticity vector is equal to R vector plus S vector. So therefore, it means that the verticity vector does contain a rotation vector and a non-rotational shear vector. So moving on to the verticity magnitude in principal coordinate, this is the representation of it. And just from looking at it from here, we can see that it includes 3 shearing components and 1 rotational component. So again, for all of the verticity stuff that we looked at, they all contain rotation and shearing components. So we definitely say that, verticity is not necessarily or generally rotation. So moving on to the next part, we're going to look at comparison of verticity, Lyotex, and shear behaviors in boundary layer transition. The first thing we're going to look at is the numerical data structure for the DNS simulation that I used to run the data. And so first of all, our grid domain for the DNS is 1920 times 128 times by 241. And the DNS parameters are as follows. So this is the Mach number, which is 0.5, the realist number, which is 1000. This XIN is the distance between the leading edge of flat plate and upstream boundary of the computational domain. This value here is the inflow displacement thickness. Lx is the length of computational domain along x direction. Ly is the length of computational domain along y direction. Lzin is the height of inflow boundary. Tw is wall temperature, and T infinity is the free stream temperature. Now this diagram here shows how our data or the Vortex structure will look once we run the DNS code to get our simulation. Now this is an example of a Vortex structure in boundary transition using modified Liutex omega. As you can see, like it begins to form at this point here. And as it goes forward, so it's moving from laminar flow to transitional flow to turbulent flow. And in turbulent flow, it's very chaotic and complicated. This view is a bird's eye view of it from the y direction. And we can see, again, looking at the laminar flow where the vortex structure hasn't formed yet. And it's beginning to form here in transitional, where we can start to see the hairpin vortex rings begin to form. And then, of course, in the turbulent flow, we have many vortex rings or many vortex structures appearing and forming. And in this area, like I said before, is more chaotic and complicated. Now, this is a video that shows the progression of the flow of the vortex structure over time over time. So as you can see, we go from laminar to transitional and then of course to turbulent flow. So using the DNS simulation of boundary layer transition, we will first investigate the behavior of shear, Lyotex, and Verticity from laminar flow to turbulent flow. And then we'll also analyze the effect of shear on Verticity. For the statistical analysis, we performed it over the whole grid domain and across time domain T. The statistical integration formula is as seen on the screen. Is this formula here where rho I j k t represents a point in the grid, I equaling the 1 I equivalent 1 to 1,920, J equivalent 1 to 128, and K equivalent 1 to 241. And of course, the T represents the step in time. The volume ijk is the volume of the space around the point rho ijkt. This value here is actually the integration output value at the time step t. So this is the value that we will plot on our graph. The results of the direct numerical simulation are recorded. Statistical analysis is performed over the whole grid domain, and the data is plotted across time domain t for Lmag, which is Leotech magnitude component, Verticity magnitude component, and Shear magnitude component. These will be in one figure, and then we will also go for the y direction for these same components. So what we did was, because the values of Verticity was so much greater than the values of the Lyotex, we used the relative values for the integration to plot the graph. And still, of course, you can see that the Verticity lines and also the Shear line is hugging 1, which means that there's barely any fluctuation. But and it's represented is not now 0, even though during this part where how Leotex is looking around by 0, this is supposed to be the laminar flow, which should show that there's barely any vortex activity, but Verticity is showing that there is, because it's around 1, right? And this is a misrepresentation, because in laminar flow we shouldn't have any vortex activity, or very little vortex activity. So clearly Verticity is misrepresenting shear as rotation in this instance. So to see this even better, I split the graph into 3 parts with the Verticity at the top, and then the laminar flow, Lyotex and shear in the bottom. So as you can see, it does fluctuate, but very little fluctuations. As for Lyotex, we can see it goes from 0.1 to 0.6. So it had an increment of about 0.5 increase over time. And we can see that shear decreased over time for this. And this actually shows that shear and Lyotex have a negative relation to each other. So as Lyotex increases, shear will decrease. Now moving on to the magnitude graphs. Now the magnitude, what we can get from the magnitude graphs is that we could see, like how before, I said that the Lyotex increment was 0.5. It's again going to be 0.5 because the Lyotex is positive, and will always be either greater than 0. And if it's 0, then that means no rotation. And so in this point, it's going to be the same increment. But we could also tell that the increment increase in the shear value and the Verticity value is minuscule compared to the Lyotex value. Again, I split the graph so we could see it a bit better. As you can see, the Verticity mag went from about 0.84 to 0.94, which is a 0.1 increase. And the shear value went from like 0.88 to 0.94, a little bit above 0.94. So that is also a little bit more than 0.1 increase for the shear. But Lyotex increased from around about almost 0 to 0.6. So this shows that the Lyotex, values continued to increase and was able to pick up the formation of the Vortex rings. And whereas, we had a little bit change. If you were to look at it, you wouldn't be able to see it because it's very small for the Verticity. So in conclusion, Vorticity is not strictly rotation. It is in fact contaminated by shear. The effect of shear on vorticity can be very large, leading to a misrepresentation of vortex indication in the laminar flow where there is basically no rotation. When we looked at the y direction graphs, we found out that over time vorticity had little to no change in value, while Leotex increased as time progressed. The shear was observed to be decreasing as Leotex increased. This shows that the Leotex has a negative relation with shear deformation. In the magnitude graphs, we found that the increase in Leotex as time progressed is more significant than the increase in vorticity and shear. Therefore, from all of this, I can say that vorticity should not be considered as vortex. Thank you for your time, and any questions?
Thank you, Dr. Nottage. It was a really good presentation. So does anybody have any questions? Okay, so I think nobody has any questions. We can move to next presentation. Once again, thank you very much. So the next presenter of this session is by Jieming Liu, and he's going to present on turbulence generation from asymmetric Lyotex. Welcome, Dr. Jieming Liu. You can start your presentation.
Okay. Okay, thank you very much. Now, okay, thank you. Can you hear my sound? Can you hear me?
Yes, we can hear you and we can see your screen too.
Okay, thank you. Okay, so this talk I will give the introduction about the turbulence generation from symmetric Lyotex. Before the we'll give the report, I must say the other idea in this report is given by the Professor Liu. I told you, okay. All the contents can be found in this paper. Okay, so this talk I will give follow these 4 parts. The first one I will give an introduction about the Vortex identification method. Then I will show the Lyotex, and then I will give the mathematical foundation of turbulence generation, and the last I will give the conclusions. Okay, introduction. In the turbulence flow, we now many people use local vortex criteria to identify the vortex. Okay, there are many methods. All these methods come from the eigenvalue or configuration of velocity grading the tensor. For example, the Q quantization, delta quantization, lambda CI quantization, and lambda 2 criteria, omega method, and Liutex or Liutex. So there are many different methods to identify the Vortex. So, but what's the difference between these criteria? I think many reporters have give detail the introduction before in this meeting. So, okay. But all these local vortex criteria involves possible physical arguments in their derivations. Their connection to vortex trajectory motion can only be established close enough to steady or slowly varying stagnation points. In fact, all these methods be used, for example, ring Q method. You must give threshold to show the isosurface. So so we use instantaneous neighbor surface to express the vortex. Okay, so maybe different value give the different realization, and all this method is not stressful free, but Liutex best definition and identification of Vortex core center lines give a threshold free and unique vortex definition. I think this is the main advantages of the Liutex method. Liutex is a vector. Its direction is defined by the real eigenvector of velocity grading the tensor. Its magnitude is defined as the angle speed of rigid rotation. The explicit Liutex best can be defined by this one. Here, I denotes the eigenvector, and the lambda r means the real eigenvalue. Okay. From the Dr. Go and Dr. Liu's research, they give the Liutex tensor decomposition. Through approximate rotation matrix, the velocity gradient can become this form, and the rigid rotation can be explained by this tensor, and the shear and the shear here is the shear and this strength along the main axis. So this is the Liutex definition and the Liutex tensor decomposition. In this talk, I will give the mathematical foundation of the turbulence generation. So the third part, I will show some mathematical foundation. For here, first we consider introduction of 2D shear and Liutex. So this is a simple 2D laminar channel flow solution. For example, we consider the exact solution is U equals 1 minus Y times 1 plus Y, and the V equals 0. Here UV is a component of the velocity, and then we can get the partial u over partial x equals 0, and partial u over partial y equals minus 2 negative 2y. And so from this special example, you can get a Liutex. For this Liutex r equals 0, because there is no for 2D laminar channel flow, there's no vortex near the boundary. So we can get the Liutex r equals 0. So now we can see now we think the induction of 2D shear and the Liutex. So if we have a pure shear tensor in 2D, for example, 0s 0 or 0s 0. If we add the shear tensor to the gradient of the Verticity, so we can get 2 different tensor. The first one is this, and the second one is this. We can find the difference of here and here. So for this thing, example, r at the beginning r equals 0, but now we add a pure shear tensor in different form. We can get we can find for this case. So for this one, shear does not generate the Liutex, because the Liutex, we take the minimum of this one and this one. So absolute of this one and there. So we can the minimum is 0. So for this one, shear does not generate Liutex, but the second one you can find if S is a small magnitude, we can find this one will generate Liutex, because for this one Liutex is not 0. So this clearly shows shear may or may not generate rotation depending on the shear direction. If both disturbance shear includes the large element of the base shear Liutex, there is no change to the rotation stress. If the disturbance shear decrease the small element of the base shear Liutex, the rotation stress will be reduced. So this is the first example. Now we consider the second example, the interaction of a shear and a rigid rotation. So for the rigid rotation, the tensor is this one. If we consider shear like this, so we add them together, we have the tensor. Now we assume omega is positive. Then we will have 2 totally different cases. The first one, if S is positive, if S is positive, omega is positive too. So R will have no change no matter how big S is, or according to the definition of R equals 2 minimum, because now R still equals omega. But if S is negative, we will have several possibilities. The first one, if S absolute S less than omega, then because S is negative, so now the Liutex R equals 2 times omega minus absolute S. If absolute S equals omega, then this one equals 0. So now Liutex becomes 0. If absolute S larger than omega, So because the sign is same, so I still 0. So from this example, we can clearly find the interaction of shear with radius could cause no change if disturbance shear has the same direction as the rotation, or reduced if the shear has the opposite direction against the rotation, or make the fluid rotation stopped. So, the shear from this example, you can find that the shear can change the rotation, or will not change. The third example, we consider this example. If the velocity the gradient of the velocity is this one, and we add another shear. So if we assume omega and S1 are positive, so we can have if S2 is positive. So now if S2 is positive, S1 is positive, so we add them together, the Lyotex still equals to omega. So now we add the shear like this one, the Lyotex will not change. If S2 less than the other, but this S2 less than S1, we still get R equals to omega. So Lyotex still no change. Because S2 less than the other, and S2 less than S1 absolute. So here we can find omega plus S1 plus S2 still larger than omega. So minimum then we can find the Lyotex still will not change. So, but if S2 less than the other and follow this one, and if omega plus S2 plus S1 greater than the other, we can get R equals this one, right? This one, because now omega plus S1 plus S2 we are greater than the other, and it absolute less than omega. So now Lyotex will become this one. Otherwise, Lyotex will become 0. So now we can find from these examples, you can find several questions and answers. The first one: does shear change Lyotex? Yes, the shear will change Lyotex, but in some cases, shear will not change. So if shear has some has same sign as the rotation strength will have not changed. If shear has opposite size but S2 less than S1, the rotation strength will still have not changed. Only if shear has opposite size but at S2 greater than S1, the rotation strength will change. So from these examples give us a clue that the interaction of shear and Lyotex is not reversible. The increase of shear does not increase the strength of rotation if the large element is increased, but decrease may reduce the strength of rotation. In any case, any change of smaller element by shear will cause the change of the rotation strength. Also, their analysis, although these are analysis for 2D cases. This basic physics of shear and the Liutex interaction should be similar in 3D cases. If we consider the interaction of shear and Liutex in 3D flows, for example, if we consider the tensor formula like this one, the tensor decomposition. This is Liutex reject rotation. This is the shear. So we add them together. The same as before. If S is positive, S is positive, it means with the same direction as rotation, the magnitude of Liutex R will have no changes because if S is positive, here we assume phi is also positive. So we add them together. So phi plus S minus phi. You should know the Liutex equals the minimum of them. So on the other hand, if S is negative, positive, opposite direction against the rotation, the magnitude of Liutex or strength of the rotation will be weakened or even stopped. Because if S is negative, so phi plus S, the magnitude phi plus S less than phi. So now the Liutex magnitude we are weakened or even stopped, because if the S is minus too large, so the sign of them, positive of them, will be same. So the Liutex will become 0. So if we consider more complex cases, for example, for interaction with shear with the rigid rotation Vortex, which is very common. For if we consider this one, we assume both phi and S1 are positive. The same conclusion will be achieved just like what we discussed about for the 2D cases. This is same for 3D and the 2D. So this is example. For example, here we consider this is a symmetric Liutex. This is another one-leg Vortex or asymmetric Vortex in the upper boundary layer. So here, this feature we choose want to show the induction of shear and helping Vortex. Because if we assume both of them are symmetric, and for example, we assume shear is clockwise, which we think S is positive, and the helping has 2 counter rotation legs. Here we first we assume helping is symmetric, or just like this one. The helping has 2 counter rotation legs. The right leg, if we assume the right leg is clockwise and the left leg must be counterclockwise. So now the helping interact with the clockwise shear. The right leg will keep same rotation strength of all same R, because the right leg is clockwise, and the shear is also clockwise. So now we add them together. The right leg will keep same rotation strength of all same R, but the left leg may be weakened because for left leg the rotation is counterclockwise, but the shear is clockwise. So the left leg may be weakened, become zero or even disappeared. This place will make the origin the symmetric helping becomes asymmetric helping, or even one leg vertex. Just like here, we can find many one leg vertex on the top in the upper boundary layer. But this figure is not clear. Maybe we should do more DNA simulation to find to get a good picture to show one leg vertex. I know there are some people's journal paper they have give clear one leg vertex figure. So this is another one leg vertex in the second level vertex rings near the wall. So this is all the contents. So now we'll give some conclusions. The first one, Liutex can represent rigid fluid reduction. The strength of Liutex L is adjusted. It is adjusted why we should take the minimum. Shear will not change R when shear and R has same direction. When shear and shear may reduce R if they have opposite direction, and the shear magnitude is larger than the origin shear contained in the origin vertex. Symmetric helping vertex may lose symmetry when interaction with symmetric shear. Helping vertex one leg can be weakened or disappeared due to the shear vertex interaction. Therefore, helping vertex is unstable in a boundary layer. One leg or asymmetric vertex are shaking, swing, chaotic, and then all them cause turbulence. The last one, the nature of Liutex magnitude, the deflation and the induction of vertex and shear is the main mechanic of turbulence generation, which is that symmetry lost and become chaotic. So this is our mathematical foundation for the turbulence generation. Thank you. So I finished the talk. So any question?
Thank you, Dr. Jaming Liu. So we can move to the questionnaires. Does anyone have any questions?
Well, I just say a few words. I believe this is more mathematical and theoretical. Maybe people will not very fully understand what to talk about. I think, well, that's the nature. That's the nature. We know that the Vortex is not a shear. But in the nature, we have both Vortex and shear. Vortex and shear can interact. Well, that depends on the direction. If shear and vortex has same direction, well, the shear did not increase the strength of vortex. But if shear is counter-rotated, shear is a direction, is a counter direction as a vortex, will reduce the strength of the vortex. Then nobody knows the shear and the vortex, same direction, not same direction, not helping. The same shear could increase, or decrease the left leg, but not change for right leg. So in this way, the two legs become one strong, the other one weak, even one weak, even only one leg. This is, I think, pretty much can be found from the paper by Mazuro, the Japanese professor. In the paper clearly show that there are many one leg helping. When you get a one leg helping, that means you lost the symmetry. It become chaotic. I believe the Dr. Jiaming Liu want to talk about that. That's the Vortex, or we say Liutex, Vortex shear interaction. Because the shear Vortex could be co-direction or counter direction. Co-direction not change, counter direction weaken. So it doesn't make the helping become unbalanced, one leg or one weak leg or one strong leg. So that's what he wants to talk about, I think. Okay. Any other people have questions? Yeah. Any other people have questions? That's more theoretical.
I must to say all the idea for this mathematical foundation is presented by Professor Liu. So I think this idea, this theory is reasonable. I think because all looks very make sense. So I think it's beautiful. The mathematical foundation for use Liutex to show the turbulent generation from the symmetrical to asymmetrical Liutex. But maybe yes, there are many different theories to show the turbulence generation. But so we or Professor Liu uses the Liutex to give the mathematical foundation of turbulent generation. I think it is with reasonable. Okay, any question?
Thank you, Dr. Jiaming Liu. You can unshare your screen.
Okay.
Okay, so our next presenter is Bu Peng, and the presentation will be on the topic of the Liutex shear interaction in boundary layer transition.
From Tsinghua University, China, and then we plan to do about the Liutex shear interaction boundary line transition. The reported proceed in series research introduction, observation and analysis and proposal. The first part is the first introduction. The development of the Vertex identification method is basically divided into two pipelines. The first category is
Dr. Bang, sorry for the interruption. But I guess I think you have two microphones on. The audio is distorted. So could you please check with that?
Yeah, we can't hear you clearly, Miss Yu Peng.
Okay.
Okay, now it's better. Right? Can you speak for some sentences?
The first category is beyond on the Stokes decomposition, including a testing method, a Q method, lambda 2 method, and the omega method. The most fundamental problem with this type of approach is that Stokes decomposition cannot represent the decomposition of flowed motion. The second category is beyond on the analysis of the velocity guaranteed tensor, including data method and the lambda C method. Both of them define Vertex as a region where velocity guaranteed tensor has two complex eigenvalues. The second generation Vertex identification method has congenital defects. Physical meaning is unclear. Vertex identification methods are scarce and cannot give direction information. Throughout selection problem, only eigenvalues are used, and the information provided by Vertex vectors is ignored. To solve these problems professionally, systematically, propose how to extract the rotation part of the region body from the followed mission and named this part as a Lyotex vector. Next, I will introduce the Vertex identification method in detail and analyze the Lyotex interaction. Vertex is a physical quality that can quantitatively describe the region rotation of fluid. Its main idea is to extract the region rotation of fluid from the fluid mission and use Lyotex to define and identify the Vertex structure. Being different from other Vertex identification methods, Lyotex has scalar, vector, and tensor forms. Its direction represents the local rotation axis, and its magnitude represents the angular speed of region rotation. In the Vertex identification method, the verticity omega is further divided into rotating part and non-rotating part. Omega is equal to R plus S, while R, S are the rotational and shear part of the verticity vector respectively. Because the rotation mission can only occur in the perpendicular to the real eigenvector VR. That is, VR is the rotation axis of the local fluid microcosm. The unit direction vector of Lyotex vector is R is equal to VR. Omega and VR volume grant them 0. Whereas the magnitude of Lyotex needs to go through two rotations, Q rotation and P rotation. Firstly, Q rotation is used to rotate the initial XYZ coordinate system to XQ, YQ, ZQ, so that the rotated ZQ is in the same direction as the rotation axis I, and the velocity gradient Tensor after rotation calls as follows. A second rotation is used to rotate the reference frame around the ZQ axis, and the corresponding velocity gradient Tensor can be read as follows. The Lyotex magnitude is divided as 12 the angular speed of region rotation. The explicit formula of Lyotex vector can be defined as follows from one study. Vertex identification method greatly outperforms the previous two generations, as merely reflected by Lyotex vector is an accurate representation of the physical amount of Vertex with a clean physical meaning. Vertex identification method solves the problem of the threshold selection for the second generation of Vertex identification methods. The Lyotex method is able to represent quantitatively the 6 elements of Vertex. Study confirmation, one has to see the role of Shear. Because of the uniqueness of the physical coordinates, we selected the principal coordinates for analyze. We define vortex identification in the principal coordinate system and analyze the influence of shearing or striking condition on vortex identification method. The principal decomposition is the decomposition of velocity granted tensor, and the principal coordinates R represents the rotation part, S represents the shear part, and C represents the striking and compression part in 3 axis declarations, epsilon, lambda, CR, and lambda I competence of either the shear part or strain part or both. Tensor et al. Studies the influence of shearing or striking on different vortex identification method. So theoretical continuation analysis, and the results are shown in table 1. From table 1, it can be obtained the Lyotex is not affected by shearing or striking. The second part is observational and analysis. Boundary line transition. I used an example. Boundary line transition is a transition process from laminar to turbulence, including lambda vortex, Hamping vortex, and Dream vortex generated by Hamping vortex evolution with the appearance of the outline high frequency range vortex. The flow of the boundary line is first disorderly. Studies have shown that the flow is affected by the unstable local hair shear during the initial stage of flow disorders. Therefore, it is necessary to study the effect of texture in boundary line transition. The observation and analysis we study from the surface slice and streamlines of the text magnitude and shear magnitude in the boundary line transition process. In Fig 1, AR is equal to 0.02 is selected as a threshold of the actual surface to show the whole transition process, while figures 1B, C are enlarged views of the transitional region and the tabular region. Fig 2 shows vortex structure and vortex line in transition boundary flow, including lambda vortex, Hamping vortex, and Lyotex lines. It can be seen that the lambda vortex and Hamping vortex, which are typical vortex structures found in transitional flows, are principally captured with the Vertex method. Figures shows that the isosurface top and the bottom views at R is equal to 0.04, as can be seen from the top view. The vortex ring structure remains symmetric, whereas the bottom view shows that the structure of the vortex appearance disordered and begins to become unsymmetric. Figures 4 represents streamlines perpendicular to the axis. It is found by observation the cross sectional streamlines crossed at x is equal to 590 and x is equal to 619. That the structures of vortex have some current regularity and correctly. Fig 5 shows the surface of a boundary line transition as is equal to 1 on the plan. And Fig 6a shows the surface of R is equal 0.04 and S is equal to 1 in boundary line transition. Fig 6 B, C are enlarged views of the transitional region and the turbulent region. Compared with the Fig 1, the shear line is mainly concentrated in the near wall area. In Fig 7, the control size shear herring coincide with the Vertice, which indicates that shear affects rotational strings. Fig 8 shows the isosurface of Lyotex magnitude and shear magnitude as the same volume during regular boundary line transition with the increase of x values. The distance between the occurrence of high strings Lyotex magnitude currently becomes shorter, which indicates the shear can affect the rotational string. Observing Fig 9, it is found that there is a sequential process of changes logging and the rise of Vortex. Therefore, we select the region where the three Vortex rise relatively gently and analyze the test of shear with the hair height of the surface of Lyotex magnitude along the z-axis in the region. By observing the section views of the three shear layers with different x values, it is found that the shear is mainly concentrated at the height of normal than 4. In the z-axis direction, the height affected by shear increase. By observing the section of Lyotex magnitude with three different x values, it is found that the Vortex structures increase and the height along the z-axis increase. The last part is conclusion. Finally, according to the analysis of the value to pass, the following conclusions can be summarized. The text is exact mathematical definition of float rotation of Vortex. It is only a physical quantity that correctly represents the magnitude of float rotation of Vortex, and it can accurately capture Vortex to the structure of Vortex increase and have a center regularity, regularity and centrally in the boundary line transition. Shear can change the rotation string, but does not mean Vortex is contributed by shear, which can be seen clearly in the formula of the Vortex magnitude. Last, shear is mainly concentrated in the nearest well air. The hair is between no greater than 4. That's all for my report. Thanks for your attention.
Thank you very much, BU Pang. So I think we are done for this session, and the next session will start since there is no the session break. And yeah, sorry about that, but the questionnaires, do anyone have any questions?
Well, yeah, let me make some comments. Yeah, it looks like you give detail about the flow transition, but what I suggested is it sounds to me your vertex structure pretty much is still symmetric. So it's hard to say the symmetric is turbulence. So turbulence is chaotic. So what I suggested, you need to increase your disturbance at the inflow. That means if you give like 1%, now we should give 3%, especially for the 3D perturbation. But it's because 3D more critical. Yeah. More critical. So then you possibly find more convolutions. Because so far, as I see, your graphic most like symmetric. Yeah, we didn't see chaotic anti-symmetric happen. Yeah, that's caused by the disturbance, inflow disturbance. We all know that turbulence is very sensitive. So where and when general turbulence is completely determined by the inflow. So the inflow, even for flat plate, of course, for different shape could be different. For the flat plate, completely depend on the inflow. So you be careful with the inflow disturbance. That's one of my suggestions. Thank you.
Very good suggestions, Professor Liu. Yes, and let me make some comments. Ms. B. Pang has just become a graduate student for 3 months, and she began to do this work for just 1 month. So, for this 1 month, she learned how to use post-processing software and begin to explore the interaction between Lyotex and Shear. And I think your suggestion is very good, and we will try to do more analysis, especially in the turbulent region of boundary layer. Thanks for your suggestion. Thank you.
Thank you, Jeff.
Thank you, everyone. So this session will end and the next session will start. The next session will be led by Ayush Bhattarai. BU, can you unshare your screen? Thank you.
Okay, thank you, Visual. So hello, everyone. My name is Ayush Bhattarai, and I'm going to be a host for session 8. So before we start, let me make a quick announcement. So in session 8, we're going to have 3 presenters, and one of the presenter won't be able to present due to his personal reasons. So our second presentation is canceled. So with that, our first presentation is going to be given by Song Jeo from Inner Mongolia University of Science and Technology, and his presentation title is Research on Vortex Structure of All Oxygen Mild Combustion Reheating Furnace based on the 3rd generation Vortex identification method. So with that, I would like to request Song Jeo to go ahead and start his presentation. Thank you. Mr. Zhao, are you here?
Yeah, actually, Mr. Ayush, this is webinar host. I think we have a 10-minute break, I guess so, before the session starts. So is that fine for you to continue the session, or do you want to take the break?
We can take a break, but like in the schedule, there is no break. So I thought we just go
Okay,
ahead.
okay, fine, fine. No issues. Please start. Continue. Yeah.
Oh, Mr. Zhao, you can share your screen now. Thank you.
Hello everyone. The topic of my report is research on vortex structure of all oxygen moderate and intense low oxygen dilution combustion reheating furnace based on third generation vortex identification method. I will report from the following 4 aspects: introduction, experiment, simulation, and conclusion. First, the introduction. The first introduction is all oxygen mild combustion, which has 2 parts. One part is oxygen-rich combustion, which has the advantage of improving the combustion intensity and flame stability. But there is a big disadvantage. That is, it will generate a lot of nitrogen oxides. The other is mild combustion. Its advantages are low reaction rate, uniform temperature distribution, very low noisy, and most importantly, low levels of nitrogen oxides are produced. Therefore, our research group combined the 2 concepts to study the characteristics of combustion. The second concept is the third generation of vortex identification method. In year of 2016, Liu et al. Proposed a vortex identification method, which further decomposed vorticity into the rotating part and the non-rotating part for the first time. In this method, the vorticity was defined as the connected region where the vorticity was greater than the deformation and expressed in the relative value. The third generation of vortex identification method successfully answered the 6 elements of vortex, including absolute strength, relative strength, local rotating axis, location of vortex core, 然后 seeds of vortex core, and definition of vortex boundary. Next comes the experiment. The experiment divorce figure is shown in figure 1. The combustion experiment is carried out in a 36 kilowatt full oxygen heating furnace composed of 2 furnaces. The nozzle structure is 11 degree asymmetric jet nozzle structure, and the exhaust pipe is at the bottom of the furnace. During the hot state test, propane and pure oxygen were sprayed from the upper nozzle and the lower nozzle respectively. During the experiment, The flame front phenomenon can be observed through the observation port, as can be seen from the MILD combustion process in Figure 2. When the flame is ignited in Figure A, there is a clear flame front. As time goes by, the flame front in Figure B is obviously dispersed and becomes larger in area, and the whole furnace becomes brighter. Finally, in Figure C, the flame front basically disappears and the MILD combustion effect is achieved. Next is simulation. In the process of grade division, grade independence was verified under 3 different grade numbers. The verification results of grade independence are shown in Figure 3. By comparing the simulation results of different mesh numbers, it can be seen that mesh 730,000 is the optimal shim with both computational efficiency and computational accuracy. That is the simulation results. As shown in the temperature counter cloud diagram and the flow diagram of season J equal to 0 in the figure below, it can be seen that the high temperature air is main at 0.2 to 1 meter, and the reflex flow line in this area are relatively dense, which also verifies that this is the main missing area of propane and oxygen. Therefore, it can be seen that the high temperature area and the main reacting area of ID current movement are at the front of the furnace. According to Liutex Vortex structure cloud map Figure 6, there are many vortexes with different intensities in the initial section of the furnace. And the initial section of the furnace is a strong missing zone. The threshold value on the vortex structure identification chart of the middle and the rear section of the furnace is basically unchanged, and the intensity of the vortex structure is roughly the same, indicating the existence of weak vortices with large shims. The vortex structure in the middle and the rear of the furnace is weaker than in the initial section of the furnace. As can be seen from the vortex structure identification diagram in Figure 6, the vortex structure in the furnace is concentrated in the initial position of the furnace, which is exactly consistent with the previous temperature cloud diagram and the flow diagram. It shows that the gas mixture in the furnace can be judged by the ID current structure diagram. The ID current structure can directly reflect the ID current moment of the gas in the furnace. Liutex Vortex structure processing method is used to process the simulated data and input it into Takeplot for analysis. The Vertex core and the Vertex line, as shown in Figure 7 and 8, are displayed with threshold value of 3. The Vertex core represents the vertex structure of the intensity at the same threshold, and the vertex line is the streamline passing through the vertex core. When a certain threshold is determined, there should not be too many vertex cores in the furnace, because too many vertex cores with the same threshold intensity can intuitively reflect the vertex structure with the same intensity of vertex moment in the furnace, which is not conducive to the mixing of combustion gas when the vertex core structure in the furnace is very little or even almost none. It indicates that the vertex structure of gas vertex moment in the furnace basically has no such strength, and there is no flow gas backflow to promote the mixing of combustion gas, and the combustion effect is very poor. The last part is the conclusion. Through the combination of numerical simulation and experiment, the eddy current structure in the heating furnace is analyzed by Lyotex method with the third generation of eddy structure identification method, and verified by temperature isoline Clyde map and flow chart. The following conclusions are drawn. First, Lyotex Vortex structure can intuitively reflect the vortex motion of gas in the furnace. Vortex motion in the furnace is mainly concentrated in the initial section of the furnace. The size and the quantity of vortex structure in this area is stronger than that in the middle and the rear of the furnace, and is also the main combustion area of the furnace. Under certain threshold conditions, too much or too little vortex core structure in the furnace will affect the combustion efficiency. The combination of vortex line and straight line can better reflect the backflow and the mixing of gas in the furnace, and is more conducive to the analysis of vortex motion of gas in the furnace. That's all. Thank you for watching.
Okay. Alrighty. Thank you very much, Dr. Chow, for your presentation. So if there is any question, please go ahead, unmute your mic, and you can ask your question. Okay, so I think we can move ahead to our next presentation. So our next presenter is Young Ding from Soochow University, China, and the title of this presentation is Liutex Shear Interaction in Turbulent Channel Flow. So Mr. Ding, you can go ahead and start your presentation. Thank you.
Can you hear my voice?
Oh, yes, we can hear you.
Okay.
Wait.
I'm Yuanjing from Suzhou University, China. My report is about Liutex and shear interaction in turbulent channel flow. My report includes 5 parts. The first is review of the first generation Vortex identification methods. The second, review of the second generation Vortex identification methods. Third, Vortex recognition method based on Liutex. Fourth, observation and analysis. Fifth, conclusion and future planning. The first part is about the first generation Vortex definition and identification method. It concludes definition and identification methods and some defects. Based on the concept of Vortex element put forward by Helmholtz, Vortex is defined as vortex tube in a broad sense, and the magnitude of vorticity is defined as the intensity of vortex, rotation intensity, which is classified as the first generation vortex definition. The first generation of vortex identification method is simply to use vorticity to represent the vortex or capture the vortex structure. However, vorticity and vortex are two completely different concepts. Both are vectors, but the direction and magnitude are different, and the equal sign cannot be drawn. In the direct numerical simulation results, Wang and Liu found that not only the vorticity and the direction of the vortex are completely different, but also there is a region with strong rotation but small vorticity, and the vorticity around it is very large. Therefore, vorticity cannot be used to represent and identify vortexes. The second part is about the second generation vortex definition and identification method. It concludes definition and some methods brief introduction. Because the first generation vortex identification method based on vorticity cannot accurately display and capture the vortex structure, many new vortex identification methods have been proposed, including Q, lambda2, delta, lambda Ci, omega, and so on. Although their theoretical bases are different, they are all uniquely determined by the eigenvalues of the local velocity gradient tensor, which can be summarized as the second generation vortex identification method. The characteristic equation of the velocity gradient tensor can be written as follows, where P, Q, and R are Galilean invariants of the velocity gradient tensor. Lambda 1, lambda 2, and lambda 3 are the 3 eigenvalues of formula 1. The Q, lambda 2, and omega methods can be roughly understood as modifications to the Koji-Stokes decomposition, where delta and lambda Ci are obtained according to the influence of the velocity gradient tensor on the local instantaneous streamline. The third part is about the vortex recognition method based on Lyotex, concludes generated background definition and some advantages. So there are 3 points about the generated background. 1, the second generation of vortex identification methods are scalar and have magnitude but no direction. Obviously, the vortex should be of magnitude and direction, and it should be a vector. 2, because the second generation vortex identification method is scalar, it depends on the artificial threshold. Different thresholds will lead to different vortex structures.
3. The second generation Vortex identification method is contaminated by tension and compression shear to varying degrees. So, to solve these problems, Professor Liu and his team proposed the Liutex vector. Liutex is defined as the rigid rotation part of the local fluid motion in the flow field, and its direction is the real engine vector of the velocity gradient tensor, which represents the local rotation axis, and its magnitude is twice the angular speed of rigid rotation. Its explicit formula was put forward by Wang and Gao et al., where the vector R is the real engine vector of the velocity gradient tensor. Lambda CR is the imaginary part of the conjugate complex engine value. There are 4 points about the advantages. The one, Liutex is not only a Vortex identification method, but also a physical quantity with direction and magnitude. 2, Liutex vector systematically and uniquely gives a method to extract the rigid rotation part of the flow field, which solves the problem of shear contamination in the second generation Vortex identification method. 3, the third Vortex identification method solves the problem of threshold selection of the second generation Vortex identification method. 4, the 6 elements of the definition of Vortex are answered. The fourth part is my observation and analysis. From Figure 1, we can get a general idea of the distribution of shear and the magnitude of Liutex in channel turbulence. In Figure 2, it is found that the drawn Liutex line can coincide with the Vortex structure, which shows that the Liutex line can accurately capture the Vortex constructors. Figure 3 shows the top view of Verticity, shear, and the magnitude of Liutex. We can see that these 3 physical quantities are roughly distributed in a strip along the flow direction. That is, it is less distributed in a certain area, but more in its adjacent areas. Figure 4 shows that the shear is mainly distributed near the upper and lower wall, and the closer it is to the wall, the greater the shear value. It is distributed within 0.4 of the wall. In Figure 5, it is found that when the components of the magnitude of Liutex and vorticity along the flow direction are the same, the coincidence degree of the magnitude of Liutex and vorticity is higher in some regions, such as the loft figure, which indicates that the vorticity in this region is less affected by shear. On the contrary, the figure on the right shows that the area is greatly affected by shear. Figure 6 is similar to Figure 5 when the magnitude of Liutex and the vorticity are the same. The vorticity is affected greatly and slightly by shear. From Figure 7 to Figure 11, the components of the magnitude of Liutex, shear, and vorticity along the 3 directions of XYZ are compared in different sections. Figure 7 and 8 are color nephrograms perpendicular to the flow direction. Figure 9 and 10 are parallel to the flow direction. And Figure 11 is perpendicular to the normal direction. It was found that the nephrograms of vorticity and shear coincided with each other, so no matter which direction, the vorticity is affected by shear to a large extent. Furthermore, Lyotex is not contaminated by shear. The last part is my conclusion and future planning. There are about 5 points. 1, the Lyotex line can accurately capture the vortex structure. 2, in the channel turbulence, the vorticity, shear, and the magnitude of Lyotex are roughly distributed in a strip along the flow direction. 3, no matter which direction of the XYZ, the vorticity is greatly affected by shear. 4, the shear is mainly concentrated near the upper and lower wall, and the closer to the wall, the greater the value. 5, Lyotex is not contaminated by shear. Next is my future planning. In fact, conclusions lack of direct numerical simulation and correlation analysis. Moreover, the correlation analysis between Lyotex and shear at different times can be studied in the future. That's all my report. Thanks for your listening.
Okay, thank you for your talk. So is there any questions for Mr. Sting? Okay, so looks like that. So this presentation ends our session 8, as well as this is the final presentation of the day 2. So we're gonna meet tomorrow at 1 p.m. Frankfurt time for our day 3, and that's the final day as well, starting session 9 at that time. So we hope to see everyone tomorrow. Okay. Thank you very much for your time and your contribution. Okay, thank you.
Okay, thank you, everybody.
Thank you. See you tomorrow.
See you tomorrow.
You can just stop sharing your screen. Yeah, perfect. So once again, I thank you all for your cooperation for today, and especially I thank the host for organizing the program very well. Thank you.
Thank you.
Now we are closing the webinar workshop on the day 2, and we'll be continuing it. Thank you so much. Bye-bye.
Bye-bye.
Bye. Good day, everyone.
Yeah.